the first day we have Professor Rob Wilby from Loughborough University, who will teach us something about statistical downscaling, about the technique, about how this technique can be applied. And we all have downloaded and installed the software that Professor Rob shared with us. So without any further ado, please, Rob, the floor is yours.
Okay, thank you very much, and welcome everyone. It's really good to see you. It's a shame that we can't all be together in one place, but I think we all understand that everyone's health and welfare is the most important thing. So we have to be kind to one another today. It's a busy day. We've got lots to cover. I'm almost certain that there will be some kind of technical problem or issue at some point. I live in a small village where the internet link is not great, so we might lose each other. So let's just be kind to one another throughout the day and just do the best we can under the circumstances. I'd also like to invite you to put questions into the chat box as we go along. If I'm going too fast, or I haven't explained something well, or you just have a question because you're curious, then please just put it in the chat box. I want this to be as interactive as possible. We're going to cover a lot of ground today. One day in which we're going to cover essentially a scientific base that took me 25 years of work. So I'm going to squash 25 years of experience into one day. So that's a lot for anyone. But I'm hoping that through the primer talks, through the practicals, and through the discussion sessions, there'll be an opportunity for you to genuinely ask and challenge and question some of the ideas that I'm putting before you. And then, of course, no Wilby training session would be complete without a quiz at the end of the day. So get ready for that. Let's see how well you can do in the quiz session, just that there's a bit of light relief at the end. So let me just now try to show my slides, and we'll begin. Okay. Okay, could Biljana or someone in the room just confirm that you can see my slide in PowerPoint display? You're not seeing the presenter version. Could someone just unmute and confirm that you can see everything okay? Okay. It's all good? Yeah. All right, thank you very much. Now then, statistical downscaling. What's this all about? Well, to set the scene, I've got 4 images here which I obtained for different locations within Serbia. And I put these up to contrast the different types of environment and situation in which we might want to understand climate change at the local scale. So if we were wanting to investigate how the climate of mountainous regions might change, clearly we need a technology that can be sensitive to the very local variations in altitude, even snow cover, land cover variations. Or perhaps we're more interested in a lowland wetland, or we're interested in modeling floods over large river basins, or finally we might be very interested in the temperature within urban areas, or even the air quality in urban areas. These are all potential applications of downscaling, where we're trying to take information from the global scale about climate change and bring it down to the scale where people are, essentially, where the problems, the issues, and the concerns are that we have. Now, here's the provisional lineup for today. So I'm going to begin with an overview of statistical downscaling techniques. Then we'll have a break and move into the bulk of the morning, which will be around hands-on exercises with my statistical downscaling tool. After lunch, we'll have a question and answer session, another talk demonstrating how the technologies can be used in practice. And then we'll move into a broader discussion in which I want us to move from the detailed technical considerations to wider questions about how we should apply these technologies most effectively in a decision-making context. So we'll be taking a much broader view of where do these tools sit within a broad framework of decision-making. And then finally a quiz at the end, just hopefully for a bit of fun and to see how much you've learned from me during the day. Okay, so let's just begin then from the start. So there are lots of definitions of statistical downscaling, but this is the one that I have in my head. And it's essentially a set of technologies that take information from the very large scale, the climate model scale, where an individual climate model grid box might be 1, 2, 300 kilometers at this scale, and bringing that down to a much more local scale, which might be a single point or a much smaller gridded area. And essentially, statistical downscaling is about creating empirical relationships between the large scale and the local scale. And the other point to note, and I put this in brackets, is we're not just thinking about weather variables for the downscaling. We may be interested in other variables like air quality or the height of a storm surge on the coast, or other variables which depend on the weather but are not weather themselves. So statistical downscaling can help simulate those kinds of variables too. And the conventional way people have done this is very much what we call a top-down framework. So the mindset, the way of thinking about this is to begin with the climate model at large scale and cascade the information, perhaps through a regional climate model, which you'll be hearing about tomorrow and over coming days, which might operate at 10 kilometers or even more recently at 1 or 2 kilometers. But we're trying to bring information down to the scale of our cities, even our streets, sometimes to the scale of the weather station, the rain gauge, and sometimes in some applications, right down to the point scale, because we might be wanting to model, for example, soil erosion in our mountains. So we need very localized information about the rainfall. And the key thing is that much of this research and development has focused on providing techniques to support climate impact assessment. So that has been the primary motivation historically, to take large-scale information, bring it down locally to help us understand what the impacts of climate change might be at the scale where people are, and at the river basin scale or at the coastal zone scale, the scale at which decisions are being made about adapting to future climate change. I just put this slide in as a note that downscaling in the broadest sense has now moved from the sort of scientific arena very much into the public arena. So, for example, in the UK, we have this website hosted by the BBC, which allows you to type in your address and up pops the latest climate change scenario, in this case for winter rainfall changes. into the future under current conditions, 2 degrees of warming or 4 degrees of warming. So it tells me that where I live, if there's 4 degrees of warming, I could see 39% more winter rainfall than at present. Now we can debate the validity of these kinds of tools in terms of the scientific credibility, the fact that there are no uncertainty bounds given, just one number estimate. There are lots of things we can say about this, but the point is that downscaling has entered the mainstream, and it's helping to connect climate scientists with the broader public using tools like this online. So let's just provide you with an overview of the main groups of downscaling methods. And this is very much my own classification of techniques. Other researchers have grouped downscaling methods into other types of family, but this is an organization of the techniques that reflect the tools rather than the statistical algorithms that sit beneath them, and I'll explain that more later on. And essentially, as we move from the top of the table to the bottom of the table, we're increasing the complexity of the technology. We're increasing the resource and the equipment demands needed to perform these different types of downscaling. But I think there are generally 4 main groups that we can identify. So we might begin with what are called, perhaps unkindly by some, unintelligent downscaling. So this is where the downscaling method does not require any information on the part of the physics, the physical processes that connect the large scale to the local scale. So the simplest version of this is to simply interpolate information, and I'll give you an example later on. There are bias correction techniques that again require very little physical understanding or climate science to perform. We're going to be concentrating this morning on these 3 main groups of statistical downscaling: weather pattern classification, weather generators, and transfer functions. And then, as I've said to you, tomorrow you'll be hearing about dynamical or regional climate modeling as another technology for downscaling from the large scale to the local scale. But the important thing is to recognize that there are increasing complexity from here to here, increasing data demands, increasing in some ways skill sets as well as we move from here to here. So an important point for potential users of downscaling is what are the resources and the capacities available in the country or location seeking to do the downscaling, because not everyone has access to high-end computing facilities, large data sets, or the statistical or physics know-how to apply some of these technologies. And that's a point I want to emphasize as I go through the day. We're looking for an appropriate technology given the local circumstances and the questions and the types of issues being addressed by the downscaling. So understanding why we're doing the downscaling is an important point to keep in mind. So let's just begin by, again, acknowledging that this is a technology in terms of statistical downscaling that has been around for at least 30, 40, maybe even 50 years now, but from the 1990s onwards was primarily motivated by the desire to serve impact scientists. So those scientists who are trying to understand how climate change at the global scale might manifest itself locally and produce local impacts on water, ecosystems, health, agriculture, transport, and so forth. So very much impacts orientated. Later on, I'll explain that now we're looking to these techniques to support our adaptation thinking, which is going beyond the assessment of impacts and involves more sophisticated use of these tools. So the roots of statistical downscaling are very much in numerical weather prediction, where essentially you have a weather forecasting system. Even today will give you information about what the weather is going to be like in Novi or where I live outside of Nottingham. I can look on my phone and it gives me very localized information. And those systems use different types of downscaling, but the early ones began by taking statistical information from the large-scale weather model and relating that to the local weather conditions at a station historically. In the 1980s, we have the emergence of some of the first classic downscaling, statistical downscaling studies, and the proof of the concept, working out what methodological steps are most important. And indeed, through the 1990s, we saw the growth of lots of comparison studies where people were taking downscaling method A, B, C, and D and comparing them against each other, almost like a beauty contest to decide which one of these performs best under which circumstance. And we actually learned a lot in the 1990s about how to go about doing statistical downscaling in the most robust way. And then at the turn of the century, there's been a much greater emphasis on understanding the sources of uncertainty in climate change scenarios. Then the following decade, we saw a move to understand how we can use these tools to evaluate adaptation decisions, how we can use them to stress test systems to see how they perform with and without adaptation. And now most recently, we're seeing the emergence of statistical downscaling methods that not only improve the resolution in space, but they also add value by allowing us to predict at much, much finer timescales. So in the past, much of the downscaling has concentrated on a daily resolution. Now we're seeing techniques that allow us to estimate sub-daily rainfall and temperature properties statistically from known scaling relationships across time. And I will just provide some examples of that later on as well. So before I start with going into a little bit more detail on each of those technologies, does anyone have any questions so far? Okay, all right, so let's just begin then with the unintelligent downscaling, which is illustrated here in this map. So if we wanted to take the output from a climate model, typically now it would be about 1 or 200 kilometers resolution for each grid box. And the simplest way of downscaling would be to just interpolate between the points, between the gridded values in space. And we can do that in all sorts of GIS type frameworks. But straightforward spatial interpolation might help us to produce a nice map like this, showing changes in rainfall across Yemen by the 2050s under different scenarios, but it doesn't recognize the important controls exerted on the weather and the local climate by things like the topography, the height of the ground, the distance from the coast, and other factors. So unintelligent downscaling where we simply smooth the data from a climate model, it is appealing at face value because you can produce these maps with a apparent local precision, but you are missing lots of important information about the control of elevation, especially on rainfall in space and time. So there's a big cautionary remark that is attached to this kind of approach. One method that has been used a great deal recently is bias correction. Some people call this downscaling, others maybe not, but it's essentially a technique for statistically scaling the information from a climate model, here shown in the top right, and just using a straightforward scaling relationship that corrects for the bias between this and this scale. And when you apply that bias correction for the error between the two, which might be in the simplest way a ratio, you can actually produce patterns that look remarkably similar to those of the observations. And indeed, this very simple method performs comparatively well with the output of regional climate models, as we've shown here. This study by Schmidli et al. was a real classic one that was one of the first to show just how far you can get with bias correction, even in a complex environment like the Swiss Alps, where you have very extreme variations in elevation. But one of the problems that we have with these kinds of bias correction methods is, what do we do about values that lie outside the range of the observational data? Quantile mapping is a form of bias correction where we take the percentile of the large scale variable. Here it might be geostrophic airflow or the strength of the wind over the whole domain of interest, and we might be wanting to relate that statistically to the strength of a gust at a very local point, in this case Changi Airport in Singapore. This here would be the first percentile, the second percentile in both the large scale and the local scale. And then at the top right, we have the 100th percentile and the 99th percentile. And we can build an empirical relationship between the percentiles in these two sets. And you can see that there's a very convincing fit. In this case, we're assuming a polynomial relationship between the large scale and the local scale. And the advantage of this simple approach is that you can apply it to any distribution that you like. You don't have to make assumptions about the normality of the data. The data can be mixtures of distributions and all sorts. But we do have a problem. What happens if, for example, we have a geostrophic airflow of 10 hectopascals in the future? Is it okay to simply extrapolate from this and imagine where this relationship might go at a value of 10? Or do we just assume that values outside the range are equal to the maximum that we've seen historically? There are lots of rules that we can invent for handling those large events, and I'm sure I think Manfred is with us. He would have a strong view about how can we reasonably extrapolate beyond a relationship like this. Well, in my view, we can't unless we've got some physical basis, physical reason to say how this relationship might extend beyond the range. So that's a significant limitation of bias correction technologies, and to a certain extent it applies with some of the other statistical downscaling methods. How do we handle conditions that are way outside the range experienced during the calibration period. And we'll see later on that sometimes the technologies can handle this if the information that we're putting into them can help us understand how the weather patterns are changing in the future. Now then, to the statistical downscaling, which is the sort of the focus of our attention this morning. Again, I want to emphasize it's about taking information from the scale of a global climate model and relating it to the scale of, in this case, individual weather stations across Morocco. And for those of you who are new to this subject area, I'd encourage you to look at the IPCC guidelines that are provided here. And by the way, when you receive the sets of slides, you'll have all of them containing the hyperlinks. So if you click on each of these hyperlinks, it will take you directly to the paper or resource. So no messing around trying to find this in the literature. And you might be thinking, well, oh, that looks a bit old. 2004, I think it was published. But actually, our understanding of the strengths and limitations of statistical downscaling haven't really advanced much in the last 20 years. We don't know much more now than we did 20 years ago. There have been different types of statistical downscaling study in different locations, but the core of the approach is still very much the same as it has been even 20 years ago. And I would suggest that there are 5 good reasons why you might apply statistical downscaling. So if you're sitting in your room and you're thinking, is this a technology for me? These are the questions to ask yourself. Am I interested in understanding the climate change at a very small or local scale? So that might be within a city, within a river basin, on a small island state surrounded by ocean. Am I interested in really small scale phenomena and potential changes? That's the first question. Secondly, am I interested in climate changes in parts of the world where there are huge variations in topography, where the landscape is very complex, where the climate of one valley might be very different to the climate in a valley next door. So you need to be able to represent that local heterogeneity within your climate scenario tool. Thirdly, am I interested in simulating localized extreme events like high intensity rainfall, extreme temperatures, local wind gusts, local storm surges, local air quality extremes? Fourthly, am I interested in variables that aren't necessarily produced directly by global climate models or by regional climate models? So, for example, you might be interested in wildfire risk or drought, and you could use the downscaling to directly simulate a drought index or a wildfire index, a measure that you can't necessarily extract directly from a regional climate model without some post-processing. Or you might be interested in dust in the atmosphere. Again, something that some climate models and regional climate models contain, but others don't. And then finally, do you want to produce very long simulations or very large ensembles to explore a huge range of plausible conditions in your decision-making context? These very long experiments or very large ensembles are sometimes quite costly to produce by other technologies, yet can be generated in a few seconds or minutes by a statistical downscaling tool. So I think if you tick any one of those boxes, then I think statistical downscaling can probably help you. So now let's just look at the three main downscaling technologies that we have. And the first one rests on the idea that large-scale weather patterns, like we can see here, they're very much like the ones that are produced for the weather reports, provide information at a location. When we see a map like this, for example, with high pressure stretching across Northwest Europe, we might be thinking that there could be warmer, sunnier conditions in the vicinity of the high pressure. But we can also see that there are some frontal systems moving across here. So there might be some locations where there is a rainfall or a marked change in temperature. But the point is that a map like this contains a lot of potentially useful information about what is happening with the weather locally. So we can take classifications of the weather map and relate those to conditions that are being experienced locally. Now, in the UK, we are fortunate that Hubert Lamb produced a daily weather classification going right back to 1861. And so we have this incredible archive which categorizes the weather on a day-to-day basis for over 150 years. Similar classifications have been produced for Europe more generally. So across Europe, for example, the Grosswetterlagen, hopefully I pronounced that correctly, provides a similar catalogue of weather patterns. And these archives, these catalogues, provide a very powerful resource for us to relate the prevailing weather type to the conditions at our station of interest. So, for example, the three main weather patterns that we see in the British Isles are strong westerly airflows from the Atlantic, anticyclonic patterns where we have high pressure over or close to the British Isles, or cyclonic systems where we have storms coming across the British Isles. And with these archives, we can see the extent to which these weather patterns have changed through time. And here's just an example for a site in the UK where I've related the chance of rainfall on the top box to the 7 main weather patterns across the British Isles. And here, what we've done is we've looked at the available rainfall record and assigned the rainfall to days under each of these 7 main weather patterns. And we see that when we have a cyclonic weather pattern over the British Isles, at this site, there's nearly an 80% chance of rainfall on that day. It's a really simple way of downscaling from that large scale to the local scale. On the other extreme, we can say that the anticyclonic weather, there's only a 10% chance of rainfall at that site. So statistically, if we see this or this, we get very different local conditions. We can also classify the amount of rainfall that fell under each of these weather patterns, and we can see that on average 5 millimeters of rainfall happens on a wet day when it occurs across a cyclonic weather pattern, but only 1 millimeter or 1.5 millimeters under an anticyclonic weather pattern. So just from this simple classification, we have a basis for estimating how the future climate change, in terms of changes in the frequency of these different weather patterns, might change the frequency of rainfall occurrence and amount, assuming that those relationships hold in the future. And the fortunate thing is that for the LAM weather classification and the Grosswetterlagen, people have produced archives of these weather patterns for the future, produced from climate model pressure patterns. So we can take the climate model estimate of the chance of an anticyclone in 2050 and use that to estimate the local rainfall occurrence and amount, helping us to connect the time and space scales. So to sum up then with the weather typing method, what we need to be able to implement this is some way of classifying weather patterns, pressure patterns, and there are lots of ways of doing that, lots of classification methods using analogs, fuzzy clustering, self-organizing maps, Monte Carlo methods, and hybrid methods. And the strength of this approach is that it's quite easy to explain. It's intuitively sensible that there's this link between the large scale weather pattern that we understand, we see daily in the weather news and the reports. And we know when we see a certain weather pattern, what the type of conditions will be locally. So we can make these physical links between the large scale and the local scale. It's also an incredibly versatile approach. We can classify rainfall, as I've shown, temperatures, sunshine, wind speed, air quality, even the occurrence of flooding can be classified using this approach. And we can sort of reverse engineer as well. We can then say, well, what are the main types of weather pattern that are associated with the extreme events? So when we have a flood over the UK in southeast England, what typically is the weather pattern that delivers that kind of condition? So we can look backwards and see, deepen our understanding of the link between the circulation, the weather patterns, and the local impacts on the ground. But this approach only works where we have a weather classification. So that may involve quite a bit of work if you don't have a weather classification already available for your location of interest. And secondly, we can get quite large variations within a given weather pattern. So for example, for the cyclonic pattern here, the chance of rainfall on average is 80%, but that might vary between 50 and 90% depending upon the period of record we've used, or the amount of rainfall on average is 5 millimeters, but you could have some days with 20 and other days with just 1 millimeter. So it can hide a lot of variation within the weather pattern. But again, there are statistical ways for handling that variation within the weather pattern. So that's not necessarily a key obstacle. And finally, we need to recognize that the weather patterns capture essentially the dynamical changes in climate, but not necessarily the thermodynamic changes. So as the atmosphere gets warmer, that can bring about other changes locally, compared with the dynamical patterns, which are showing where one weather pattern is moving or its location is changing in space and time. So these are some of the main limitations. Do you have any questions at this point about the weather typing approach to downscaling? Okay, let me move to the second form of statistical downscaling. And this is a form of downscaling that has actually been around for over 100 and, well, about 170 years, and is based on some quite simple rules when we look at it in the most fundamental sense. So, for example, we all recognize in Europe that when we have a wet day, the chance of another wet day afterwards is relatively high. Or conversely, when we have a dry day, the chance of a dry day following a dry day is high. So in other words, we recognize that certain types of weather tend to lead to other types of weather. And that observation was first captured statistically by Quantile in 1852. And then for over a century, we've known that the chance of a rain day today is higher if it rained yesterday. So wet days, again, tend to cluster in space and time. We've also known for over 50 years that there are certain distributions that apply well to the daily rainfall amounts, which tend to have skewed distributions. So there's lots of little days of rainfall and relatively small days with large rainfall. We also know that the distribution of the length of wet and dry spells follow a geometric distribution. So there are lots of days, lots of spells that are only a day or two long, but few spells where we might have, say, 10 dry days in a row, and that follows a geometric distribution. And basically what I'm showing in this table is that through time, people have statistically described all of those things that we intuitively know and observe in Europe in terms of how rainfall and temperature behaves, and turn those into simple statistical relationships, which are now used within this branch of downscaling called weather generators. So here's an example of what this looks like in the simplest way. So if I'm looking at the rainfall record in Cambridge, and this is the daily rainfall record, I note that the chance of a dry day becoming a wet day is about 29%. But the chance of a wet day becoming another wet day next is 65%. So that captures what we know, that the wet days tend to follow wet days. Conversely, we can use the above values to work out what happens if a dry day follows a dry day. And we can see there's a 71% chance of a dry day following a dry day across the whole record. And a wet to dry is 34%. And with that simple relationship, we can produce, using a random number generator, very plausible representations of this clustering of wet and dry spells, as we see here. So the black is the observed and the red is the simulated. And you can see how this technique nicely captures these spells as they occur through time. And that's all it takes, 2 parameters to be able to do that. It's a wonderful technique. But if we're using a weather generator, we need to be able to predict whether or not it's wet or dry from day to day. And then if it is wet, how much rainfall do we have? And here there are different distributions that people might use to represent daily wet spell amounts. So here I'm just showing how each of those, 3 distributions compare with observations for Addis Ababa, the capital of Ethiopia. So what we're showing here in the open circles is the modeled value compared with the observed. And the open circles are if we assume the rainfall amounts follow a gamma distribution. And you can see that the gamma distribution for this site underestimates the larger values, or the values above 25 millimeters are too small according to that distribution. Conversely, the stretched exponential gives us values that are, sorry, I've got that the other way round. This is, I should be saying that the modeled values here are too large compared with the observed. Sorry, it's an early start here. So the gamma distribution is showing 60 millimeters when it should in fact be 40. Conversely, the stretched exponential here is showing a value of 100 millimeters for the observed and about 70 for the modeled. So it's underestimating the observations. And in this particular site, the best model is just a fourth root transformation. So the square root and then the square root again of the amount is the best way of transforming this data set and allowing us to simulate it at this site. And the point is that we can't really generalize as to which distribution is going to work best everywhere, because there may be actually mixtures of distributions at a site depending upon very different weather phenomena. So, for example, in the winter, we might have very heavy rainfall totals associated with the passage of cyclones or weather fronts across a region. And in the summer, we might have highly localized convective storms that generate very big rainfall amounts. And those produce quite complex distributions when we put them all into one data set. So when we apply these techniques, it's a good idea to work on the assumption that we need to test the best distribution on a site-by-site basis, or have some physical reasoning to justify the choice of one distribution over another. And weather generators are also very powerful for helping us to fill in data where there is no information, where we can relate the parameters of the weather generator to things that we can measure on the ground or observe from space. So here, for example, is a study in which we created a weather generator that can be run anywhere for the country of Yemen. And as you appreciate, Yemen is struggling in all sorts of ways, has relatively little on the ground data. The data sets where they exist are short, they're patchy, and there aren't many stations. So we take all of that information, put that into a weather generator, and then combine that information with topographic, the height, the distance from coast. Even in this case, when we're modeling temperature, we might feed in the vegetation cover and use that information to then estimate in a weather generator how temperature conditions might vary in space. So it's a very versatile technique for applications in data sparse locations. And this goes back to the point I was making earlier about selecting the right technique for your particular circumstances. How much data do I have? How much time? How much computing resource? How much local knowledge of the climatology do I have? These are all important considerations. Okay, so moving on then, just to the final method is perhaps the easiest one to understand, the transfer function. And crudely, this is essentially a regression-based approach where we might, in this case, for example, relate the pressure, sea level pressure at a location, in this case over southeast England or eastern England, and we might relate it to the variable of interest. In this case, it's the strength of the heat island in London. So how much hotter is the center of London compared with the outside countryside when you have certain types of weather pattern. And you can see that there's a lot of scatter here, but generally under higher pressure, we see stronger urban heat islands over this region, or when there are lower wind speeds, shown in the box at the bottom and the orange dots, the heat island tends to be weaker. And we can use either linear or non-linear relationships between those scales, and we can use multiple predictors, sea level pressure and wind speed, to then build an empirical model that relates the large-scale weather pattern statistically by regressing against the variable of interest. And this actually works quite well. Here's an example of simulated urban heat islands, strength in London in tenths of a degree. So under some conditions, the centre of London can be nearly 8 degrees warmer than the surrounding countryside. And the grey line shows the observations. The red line shows us the simulated values from this simple regression-based approach. And then the final step with these technologies would then be to say, okay, how is the pressure and the wind speed going to change in the future? What do the climate models say? And we put that information into the regression relationship. And here I'm showing for 4 climate models how the heat island might change, or the temperature might change in the city of London under these different projections. So we're taking the large scale information about the future wind speed and pressure to estimate the strength of the heat island. And this is an example where not all physical models or regional climate models would necessarily give you that kind of detailed information about a heat island intensity in a particular part of a city. So it helps you to model something that it's not otherwise very easy to obtain from other downscaling technologies. Although some climate models do now produce heat island information, but with a whole host of caveats. One of the important applications of these techniques that I'll be discussing and we'll be exploring together later is the ability to repair data sets. So here's an example where we're looking at temperatures over Tunis, and the black thin line are the observations, which you can see are quite patchy. They're incomplete. But using the downscaling technique, fitting the model where we do have the data, we can estimate the values on missing days. So this sort of technique can be used to infill and repair broken data sets. And I think this is perhaps an area that hasn't really received that much attention, because you're using physically plausible relationship between the large-scale weather patterns and the temperatures, in this case, experienced at Tunis, to reconstruct what the conditions were on days, even when we didn't have any data, or the data had been lost, or the records were broken. So then, to sum up, in terms of the transfer functions, these can take many forms. The most common one is via linear regression, but we can use other more sophisticated techniques like neural networks and kriging to relate these variables. They're quite straightforward to apply. As before, we can use these to simulate all sorts of variables that we might not necessarily be able to get from other sources. And it's very versatile. It's quick to apply, can be implemented in lots of different types of location. But we also have to acknowledge some of the big weaknesses of this method. Regression approaches without extra steps can underestimate the variance, which is important if we're interested in the extremes. Some of them may assume linearity or normality of the data, but again, with appropriate techniques, we can relax those assumptions or cope with non-linear and non-normal data. So that's not necessarily an obstacle. And one of the assumptions that indeed applies to all downscaling methods is that the relationship between the large scale and the local scale remains constant in time. And this is a key caveat that we will be returning to later. It's one where some say, well, this makes statistical downscaling a complete nonsense, and because you can't uphold this assumption. But actually, as we'll be seeing for Novisad later on, even where data are non-stationary, we can apply these techniques with care to simulate even conditions that are changing quite abruptly and markedly through time. And indeed, the assumption of stationarity is also embedded in regional climate models. It's not explicit as it is in the case of statistical downscaling, but it's buried in the assumptions behind some of the many parameters within the regional climate model, that those parameters are valid under changed conditions. So the stationarity assumption is one that applies to all downscaling methods. And it's important to recognize this if you're intending to use these technologies. So just before we break then, some key points to take away. Let's just look at this picture on the left-hand side, which I took whilst flying over a part of Central Asia. And I look down and I look at this sort of landscape and I think, wow, how is the climate going to evolve in a valley by valley, mountaintop by mountaintop basis? How would our best models perform in this kind of environment? So this really sort of focuses the mind, you know, what is the most appropriate technique to simulate climate changes in this sort of environment? And I think that here, developing relationships between the large scale and the very local scale, or even on a valley by valley basis, is one way in which we can do this. And this is where statistical downscaling can help. But we need to be very careful that we don't misunderstand the precision that we can get from downscaling with accuracy. There's a difference between being able to model something at a very precise location compared with having an accurate representation of the future climate change at that location. Secondly, with all downscaling approaches, we need to think about what's the value added? What am I getting back from all the effort of building these models? Is it worth the effort of gathering the data, cleaning the data, calibrating the models and so forth? Are there simpler ways of doing this to support my decision making? And that's, again, something I want us to discuss together as a group towards the end of the day. And finally, I think up until relatively recently, the downscaling research has been very much limited to academia. It is beginning to find its way into the public domain, as I showed you earlier, and it is beginning to inform some types of decision making. But as a generation, we've got relatively few examples of those real world applications to turn to, and that's a real opportunity for us as a community to move the thinking and the application of these technologies forward. So at that point, we will pause and see if there's any questions that you'd like to raise, and if not, we can move. Before I move to the slides, can I just confirm that everyone has installed the downscaling model and has that up and running on your laptops?
Yeah.
Okay.
Here in the classroom, we have it installed and it's running.
Okay, that's really good. I've got it running in the background here on my machine, but I'm going to be trying to walk you through the exercises using just the slides, so I don't have to sort of flip in and out of presentation modes, just in terms of the practicalities. But if we get into a real difficulty, or there's a question that someone wants solved, I can go into the tool this end and demonstrate it by coming out of presentation mode with the slides. But let's just see how we get on with that. Do we have any questions or concerns before we begin? All right. Now this is a sort of the point in the day when I really do encourage you to stop me and say, Rob, I'm completely lost, or it's broken, it's not working, I don't understand what I'm doing. If I was in the room, I would just be walking around amidst you and sort of leaning over your shoulder and pressing buttons and trying to help you that way. So we've got plenty of time to work through these exercises. And we're going to begin the process by applying the downscaling tool to temperatures in Novi as a beginning exercise. You should all have the sheet that has the 20 steps to using SDSM. You should also have a sheet which has a list of all of the variables that we can use for the downscaling and their codes and definitions. Now, the clever thing about this sheet is that the numbers, the steps, relate to the steps that I will show on the screen. So if you get lost or you're struggling to follow me, you can refer to the same step on the screen as the one on the sheet, and that will help you navigate through the process. But as I say, please do not hesitate to ask a question, stop me if I'm going too fast or something is unclear. Right, okay, let me just upload the presentation and we'll get underway. That one. That's great. Okay, so you should all have a screen like this in front of you. There's the initial splash screen, and then you move forwards and you have a screen like this, which is the sort of the master screen of the software. And before we begin, let me just sort of help you. I'm not sure, Biana, can you see where I'm moving the pointer on the screen? Is that clear? Can you see the pointer?
Yes, we can see.
Okay, great. So you know, if you're able to see the screen with my display, you can see that there are these buttons with the green arrows that run across the top, and essentially the software is built as a production line, so it takes you step by step through the main tasks of setting up, calibrating and running a downscaling model. And as I'll explain later, each of these buttons represents a task in the downscaling process. And so you think of it as a chain where you're moving from one step to the next on the way, on the path to building a downscaling model. you've met me, but you haven't met the co-developer of SDSM, who's Chris Dawson. He's a computer scientist, and for those of you who are interested in these things, the SDSM is actually written in Visual Basic of all things, and people tease me, they joke about the simplicity of the programming language and all the rest, but the great thing about it is that this simple language has enabled the tool to work effectively on 20 years of Microsoft Windows development, and it still works after 20 years of changes in the Microsoft operating system. So if you want to, a top tip here, if you want to build a tool for other people to use, pick a language that is going to be resistant to long-term changes in operating system if it's designed to work on a laptop or PC. So the original tool was developed over 20 years ago and was quite a bit different to what we have in front of us today. The original concept was to show in practice what I was doing as a researcher in downscaling. So I initially developed the tool as a way of explaining to less scientific audiences how downscaling works. And the first version took us through these essential steps in building a statistical downscaling model. And then through the years, we have been supported by various agencies to enhance the functions within SDSM to enable a wider set of applications, for example, to flooding, extreme value analysis, sub-daily simulation, and so forth. So the tool has developed over 20 years in response to user requests and demands. And so if at the end of today you have suggestions for me, oh Rob, it'd be really great if SDSM could do this, then please let me know. We're always really happy to hear from the user community how we can improve this tool to make it more useful for people who want to use it in different locations and contexts. So please do feed that back to me. Now, the current version is now, with some modifications, a few years old, and we're on the brink of issuing a new version, which will look very much the same as what you're looking at today, but it does have some extra quality assurance steps to screen the basic data that you're putting into the tool. It also can be used for simulation of sub-daily extreme values, mainly for rainfall estimation at hourly levels or even smaller, and feeding that into intensity, duration, frequency analyses, which those of you with an engineering background understand is an important application for design and testing of the performance of certain types of infrastructure. So I just put that to highlight what's coming your way, and hopefully this new version 6 will be released by the end of the year. On the in the shared folder, I've placed a number of resources. Unfortunately, the system doesn't allow me to put the reading documents in the reading folder. So you've got a folder called reading materials with nothing in it, because I didn't have the rights to move the materials in there. So sorry about that, but I'm going to highlight 4 key papers for those of you who want to do some extra reading. For those of you who really want to understand where the tool came from, there's the classic version, which was published nearly 20 years ago, which describes in some detail the equations, the algorithms behind the model. And then this second paper describes the latest version of the model and the way in which it's intended to be used in a different way. So this first paper was built at a time when downscaling was used in a let's predict the future in order to act on the future. And this paper was published at a time when we're now thinking about how statistical downscaling can be used to stress test or interrogate adaptation decisions. So it's a different way of using the downscaling technology. And again, with the slides, when you receive them later, you can just click on these links and it will take you directly to the source of the papers online. And then these other two papers, Yates et al., I'll be describing in a little bit more detail this afternoon. It's a nice case study of using SDSM in a water resource application, using the downscaling to test how a water resource system might behave in the future with and without adaptation. So it's a nice paper to illustrate how a downscaling tool can be used in a very practical context. And then for those of you that are interested in regional climate models, and you'll be hearing lots about that tomorrow, and want to understand how the statistical downscaling model here compares with the performance of a dynamical model, WRF, which some of you may have heard of. This is a recent study published by Santos and others who compared the performance of these two very different models across Spain. So it shows that A, how you go about comparing different types of downscaling model in a fair way, and B, how those different technologies perform if you're very much interested in extreme rainfall estimation. So they're the four key papers that I've placed in the folder, but you can click on the links and obtain other information along the way. And then before we get on to get started with the software itself, I thought it's interesting as well to show you that there are some interesting emergent patterns in the use of the tool, which, as I say, has been around for 20 years, which gives us an ability to look at how have people used this tool in the past, where are they using it, where are the opportunities for future research and development. And again, this meta-analysis that we published several years ago highlights some interesting research gaps which you might like to refer to if you're thinking about, well, this looks like an interesting tool, but I want to do something novel. Well, we've helped you by identifying where the gaps might be. But when we look at the meta-analysis of the users, that we've got well over 500 papers that have used SDSM so far, much more than 500. But if we look at the first 500, we see that the majority of the studies have been published in China, Iran, Canada, India, Ethiopia, and then interestingly in sixth place, the UK. So there's a huge number of users outside of the UK. And then many other countries where the tool has been used. And as far as I'm aware, no one has yet applied SDSM to a published study in Serbia. I might be wrong. If you know otherwise, then please let me know. I would love to add this to our database of studies. But I think there you have a wide open goal to be the first to use this tool in an applied way to some interesting questions, climate issues in Serbia. And I think one of the immediate tasks that you could get on with is looking at extreme temperatures, heat waves, and using the downscaling tool to understand the dynamics, the likelihood of heat waves in some of your major cities and towns, just as a suggestion. Okay, and the other thing that's quite interesting from the meta-analysis is which are the sectors that have been most favored. And like most of the downscaling literature, it's the hydrologists, it's the water guys who've been using these tools the most. And then there's quite a big gap between the amount of use by the water guys and those interested in agriculture, flooding, urban environments, health, energy, tourism, and transport. So again, you can look at this meta-analysis and think, where are the gaps? If you publish a study on downscaling and water, chances are it's difficult to really add extra knowledge or to take it beyond what we already know in the published literature. But in comparison, there's very little in the domain of health and ecosystems, for example. So again, going back to my suggestion, publishing undertaking a study of extreme heat waves and linking that to human health would plug a really big gap in the literature, and one where there's a huge amount of interest growing internationally in the links between extreme temperature, the urban environment, and people's exposure and health impacts, and the impacts of extreme heat on their health and their livelihoods, their productivity, their ability to work. There's lots we could be doing as a community in that area. And many of the studies so far have concentrated on using the tool to create a scenario. How might temperature change in the future? How might rainfall change in a given location? And then stop at that, which is fine. In some locations, this could be the first time that someone has tried to do that for their particular country because they have limited resources. So that's still important work. But I think there are also, big opportunities here to do more work in terms of the application to vulnerability assessment, or using the tool in a management decision-making context. Again, I'm showing you this to highlight the areas, the gaps in the research that we could, as a community or within EXtremeClimTwin, be addressing. Okay, now then, let's get down to the main business of the day, which is learning to use SDSM. And this rather horrible diagram shows the architecture of the software. And I want to just highlight a few points. So you can look at this screen, and the red boxes refer to the 10 or 11 screens on in SDSM. So if I skip back to the opening slide, I can see this on your master panel in the background there. Okay, there we go. All right, so you can see those buttons along the top, like quality control, transform data, screen variables. Each of those is a separate screen in the architecture that you can see here. And think of SDSM in the simplest way as a workflow. It's a workflow that takes you from checking your data quality to start with. Up here, you've got the quality control, the transformation steps, before you then start to choose which variables to include in your model, and then you build your model. Once you've built the model, you're then able to apply it either as a weather generator to simulate the historic information, or as a scenario generator to imagine other conditions beyond the historic. And then there's a whole suite of screens that enable you to analyze the results of the downscaling, whether it's in terms of classic frequency analysis, time series analysis, basic summary statistics, and some graphical comparison of the results. So that's essentially gives you the overflow of the an overview of the workflow. And there are only 2 points at which data enter this workflow. Right at the beginning, when we are looking at the observed data that we use to calibrate the model, and the reanalysis. So these are the large-scale weather pattern indices that have been prepared for you ahead of time and used as the basis for predicting the local scale phenomena. Okay, before I go any further, are there any questions or concerns about the overarching concepts or architecture?
No, there's nothing in the chat.
Okay, that's good. So again, you won't remember this to begin with, but there are essentially 5 file types that are handled within SDSM. So there's the basic data and information that's being fed in, which we use the .dat extension. There's output from the weather generator, which might contain meta information about how you set the model up, and then the actual output produced by the weather generator, and then some outputs from some of the diagnostic tools, which are text files capturing some of the summary statistics and the frequency analysis. Now, you might think this is all, you know, so incredibly simplistic. It's working with text and ASCII files, and there's a reason for that. We want this tool to be able to work in any laboratory or country on the planet where people might not have access to supercomputers or high-end computing systems. So it's deliberately built at the lowest common denominator. The other key point to note, and this is one to highlight, if you are using the model and you're finding difficulties after today, if you send me the par file, that once you've calibrated the model, this .par file, this now allows me, like a doctor, to very quickly diagnose your problem. 9 times out of 10, I can say, oh, this is simple to fix. I can see from the par file what's going wrong. Take this tablet. It will help me to diagnose the problem. So if you want to get in touch with me after today with some problems with the downscaling, please always send me the par file, and 9 times out of 10 we can quickly resolve the problem. Okay. Now, I've already mentioned the worksheet, which is designed to help you, again, after today, guide yourself through the process of setting up the tool, calibrating it, running it, and then evaluating the outputs. And we've done that in 20 quite discrete steps. Hopefully that will be a useful resource. And it did occur to me afterwards, Liliana, that maybe we should be translating this sheet for a broader audience. I mean, I know many of the, you know, in Serbia, you all have great English language skills, but more generally, internationally, we could be translating this worksheet to help users in different places.
We can do that, no problem. We can even do that maybe for tomorrow, if it's okay. We can have it in Serbian, but I don't speak any other language than Serbian and English, so maybe someone can help us with French or German. Manfred, maybe. But it's just a side thought that this might be a way of helping a broader community, picking some other languages. Okay. Okay.
Thank you. Right then. So let me move on. So first step, I'm going to turn the tables and set you a task before we even begin with the tool. In the online file, there should be an Excel work file called Novi 1961 to 2000 data. What I'd like you to do is to get hold of that data set, and I'm going to give you, let's say, 10 minutes. We can have a little bit longer if you like. I'd like to give you 10 minutes to look at that data set and apply visual and sanity checks to the maximum daily temperature series. And for those of you who attended the workshop 1 earlier in the year, or was it last year? I can't even remember. Sorry. We remember we went through a whole host of exercises for quality assuring raw data. So if you can remember some of those tasks, you might not necessarily have time to apply them this morning, but at least just write down, if you had extra time, what tests you would apply to these data before we begin modeling them. And the reason I'm emphasizing this is all of the simulations that we're going to build with the downscaling tool hinge on the quality of the observed data that we put in. We all know that saying, garbage in, garbage out. So it's really important that at the first step, we're confident that there are no problems with the data. Okay, so I'm going to give you 10 minutes to look at the data and then come back and tell me what you found in the data. Are you happy to go on with this data set in the downscaling exercise? Is that all clear? Okay, over to you then for 10 minutes. Okay, let's see how you got on. If you'd just like to put in the chat or the put your microphone on and ask the question or make the remarks. And Liliana, if you could perhaps help with this, that would be great.
There is a comment in the chat.
Okay.
Maximum temperature on the 31st of October to 2013 has the 999 value. Minimum temperature on the 24th of November 2012, the same value. Those are actually the missing values. Not sure about the possibility of 121.9 millimeters precipitation per day.
Okay, all right, very good. So just to summarize that, it looks like within this data set, we only have one missing value for the maximum temperature, which is on the 31st of October 2013. And we will come back to that later. What's the temperature range between the minimum and the maximum? Did anyone look at that?
It's quite high, from 40 degrees Celsius to minus 17.
Great. Now, does anyone question those values, or do you think that they're credible?
Nothing here in the chat. You can unmute, please, and speak up. November 24th, 2012, missing minimum temperature, but we are actually talking about maximum. Just look. Yeah. Maximum temperature.
Okay. So let's assume that that we trust the temperature ranges within the data set. We found one missing value. What other tests, if you can remember from the first workshop, might we apply to this data set to see whether or not it's trustworthy? You might not have time to apply them today, but if you had an hour or so, what other tests could you apply to this data set to confirm or check that the quality is good?
Plot the data.
Yeah. Can plot the data. What statistical tests or analytics might we apply? Okay, well, perhaps I'll just provide you with a reminder of some of the other tests that we could apply here. let's have a look. So, oops, back on the screen. So here we go. Some of the answers. We've got a temperature range of -17 to 41.6. And actually that 41.6 degrees Celsius occurred in the famous Serbian heat wave of 2007. And there's quite a bit of literature about that famous heat wave. So I trust that value. And the mean seems about right to me. And I think most of us have found this missing value. But some of the other tests that we could apply that I talked about in workshop 1 is the day of the week and number bias. So are values as you'd expect during the week? Are there more or fewer numbers than you'd expect in certain categories? We could apply the Petit homogeneity test to see if there's a break point in the time series, which could indicate a move of the station, a change of instrument, a change of observer. So, or even, urbanization or a change in the climate. And thirdly, we could try to compare with some of the nearest stations. I'm not going to attempt to pronounce these, but these were the ones that I found within the data set, which I think were closest to Novi Sad within the archive that you gave me. So let me just illustrate how these different tests would play out if we had the time to look at them. So the day of the week test is an interesting one. We can show where there are missing values. So there's only one missing value. So there's no day of week bias, which we've seen often in rainfall data where someone doesn't go and do the measurement on the weekend. And so there's lots of missing values here. There's just this one missing value. And then we can plot the frequency of the hot days greater than 25 degrees Celsius, shown in this plot. Or we can look at the frequency of very hot days greater than 30 degrees Celsius. And now we see this interesting weekly pattern where the maxima the frequency of very hot days is higher on the weekend and at the start of the week than in the middle of the week. Any thoughts on why that might be? Okay, so what we've got here is a potential aerosol effect.
Excuse me, Rob. We have a comment combining the data from Sunday and Monday. That's why the temperature is so high.
Yeah, I don't. I mean, that is often a risk with rainfall data, but the way in which temperature measurements are taken, which is someone goes and looks at the thermometer in the morning on the day and records the value. Yes, it might integrate the maximum and the minimum, but it's not accumulating a total like in rainfall. I think what we might be seeing here is a potential aerosol effect. So cleaner air on average over the weekend, and more aerosols in and around the city during the week, and that affects the solar energy receipt and might give a slight difference in the likelihood of a maximum temperature. But the important point is that this is an example of a factor that we won't be able to include in the downscaling. We don't have a predictor variable called aerosols over Novi Sad. So if this is an important factor that determines the likelihood of a very hot day, we're losing a little bit of information here. And it means that if the very hot days tend to occur on a Sunday, when the air is clean and clear and there's lots of sunlight, we might not be capturing the peak temperatures, or conversely, we might overestimate temperatures in the middle of the week because we're not accounting for the lower transparency of the atmosphere. Okay, so this is a really nice example, but I think it's a relatively small concern in this case, and as we'll see later, the model still works well despite this potential factor. The other thing we can do is the number bias. Remember from workshop 1, people like whole numbers or numbers that are divisible by 5 and 10. So if we look at the distribution of the temperatures being measured at Novi, we can see the overall distribution here in the bottom, and then I've just highlighted those values that are above 30 degrees Celsius. So people recording the temperatures at this station really like a number like 30, but they don't like a number 30.1 degrees Celsius. They really don't like numbers like 30.9, but they like 31. So there is definitely a number bias within this data set. And actually, this is quite a useful test. I was talking with Tom about this yesterday. Just this test might tell you whether or not the data were gathered by humans or by an automatic weather station. Okay, because I'm assuming that the automatic weather station doesn't care whether or not the day is 30.9 or 31. So it's an interesting way, a diagnosis to say, yes, I think this has been made based on manual observations where the observer clearly has a certain number bias. Okay.
Rob, excuse me, there is one question in the chat.
Yeah, sure.
Why is there no aerosol effect in the graph? The maximum larger than 25?
Yeah, well, you have to, that's a really fantastic question, whoever raised that. I would speculate that the really high temperatures are, as we will see later on, are caused by a combination of factors. So high pressure, low wind speeds, high amounts of sunshine, and those are conditions that favor the very high temperatures. Whereas 25 degrees Celsius is warm, but it's not a particularly remarkable value, and that can occur on days where heat might be advected or flowing from other places and relying less on extreme amounts of sunshine, solar heating, combined with high pressure and low, very limited wind speeds and things like that. Okay, so very static air masses with lots of sunshine. So I think there are different processes going on at the very extreme temperatures where I suspect, and this is just a hypothesis, that the aerosols might be having an effect. But it would be interesting to try and confirm this with independent data. Maybe another research question for the team there to think about. All right. A third test is the Petit test, which you might remember from workshop 1, which helps us find these breakpoints in the data. And when we apply that to the data set here, we see that the conditions at the end of the record are somewhat warmer. In fact, over 1.5 degrees warmer than at the beginning of the record. So our statistical downscaling model needs to be able to reflect that potential step change in temperatures. So we need to be giving the model sufficient information to be able to capture this change in temperature. We're assuming that this step change is not because of a movement of the recording station or changing in the instrumentation or something else like that. But again, we could be turning to the meta information for this weather station to see if the site has always been in the same place with the same instruments and so forth. So that might be some extra investigation that's worth doing. All right, and then finally, we can do the same tests for the neighboring stations, where we also see the petite test shows a step change, which suggests that actually we've got perhaps some regional warming occurring here. It's being the same, roughly the same change, a rise, a trend is being seen in all of the stations. And we're seeing actually for these two locations, no day of week influence. So maybe these are, I'm speculating, perhaps they're smaller places, or for some reason have no aerosol effect, better air quality, so no influence here. But again, we're seeing the number bias in the data sets, and we're seeing the step change in the temperatures. I just want to note that the version 6 of SDSM will undertake these tests. We're adding them to the tool, so you don't have to do this in Excel anymore. The tool will do the petite tests, the day of week tests, and help you diagnose these things within 2 seconds of pressing the button. So that will greatly help people using the tool in the future. Okay, now, I mean, we spent quite a bit of time looking at the raw data, but I think it's really important to emphasize that the quality of what we're going to do next depends on our confidence in the data. And it really is worth spending time checking the raw data before we try to build the model. So now we're ready to get underway. And also within the shared folder, there should be a data set called Novi SAD Tmax OBS TXT. Has everyone got that on their machine and in a location that they can access? Was that all set up beforehand? Are we in good shape? Yeah, okay. So it's a simple text file, and what I've done here is, again, to save time, I've taken the Novi SAD data and I've put it into the right format for the use within SDSM. So if you see on your check sheet in step 1, the downscaling software assumes that data files begin on the 1st of January 1948. Okay, now I won't go into why we chose this particular date, but it's a common reference point. So if your data set begins in 1961, which it does, you have to put in the correct number of missing data values to pad that file so it begins in 1948. So if you look at the text file I've created, you'll see lots of -999s in the first part of the file, and then you come to the actual observed data here with the maximum temperature values beginning in the 1st of January 1961. Okay, so that I've done that all for you, and this will provide you with a reminder. Again, this is in ASCII format to make it as simple as possible for users all over the world with different machines and capabilities. Okay, so that's step 1, prepare your input data. Step 2 is to obtain your predictor variables, which you obtain from this particular website online, linked to the SDSM software. And it's just a case of typing in the longitude and the latitude of the station here, which again is given for Novi Sad, 19.85 degrees east, 45.33 degrees north. You put that in and it will create a zip file with all the predictor variables needed to model the conditions at your location. Okay, so you should have within your, again, in your setup, a zip file called box something or other. Can you see that? Again, Jana, perhaps if you could just check and confirm, and Minucha, if you can help as well, check that everyone's got that box file set up and can be found.
It's all good.
All good.
Yeah.
Excellent. Okay, so we're already at step 2. Now then, you've got this sheet that provides you with all the predictor variables that can be used for the downscaling. These have all been prepared for you ahead of time and are held within the box file, the zip file. And you can see all sorts of weird and wonderful variables, some that we might recognize straight away, like mean sea level pressure, precipitation total or near surface air temperature. And then there's lots of other ones that we might not have heard of before, like surface lifted index, vorticity, zonal wind speeds, and so forth. Geostrophic airflow. These are all variables that essentially describe the mobility, the stability, the vertical lifting, the dynamics, the airflow across the region. You've got nearly 30 variables there to choose from, to customize your model to use the variables that makes most sense at your site. And so you might be already be thinking, you know, looking down the list here, which variables might be sensible for maximum temperature. So you might think, well, direct shortwave radiation, the amount of sunshine, surely that's got to be a factor here. So that might be a good candidate variable, and so forth. But we'll come on to that testing in a minute.
Excuse me, Rob, we have one question.
Yes.
Why is it important to have everything in 500 and 850 hectopascal?
Excellent. Again, thank you very much for that question. So the predictor variables are provided for 3 different heights in the atmosphere. So we have wind flow speeds and directions at the surface, at the 850 hectopascal level, so that's a little bit above the surface, and then at the 500 hectopascal level, that's quite high up in the atmosphere. So in other words, we're recognizing that the conditions at the location depend on weather flow, airflow, and humidity values at both the surface, the middle, and the upper atmosphere. So it's helping us to represent controls in 3 dimensions over our site of interest. Does that make sense? Okay, thanks for that question. I'll skip that one just to say that these 5 variables were added relatively recently to downscaling archive because we found when we were downscaling extreme rainfall values in East Africa, where the strength of the uplift in the atmosphere and the amount of moisture in the atmosphere are really important factors. We found that our downscaling improved massively when we had these additional variables. So these help us, some of them, to model extreme rainfall very well in a way that the simpler set of predictors wouldn't. And you've got the definitions here of what these variables are doing. Okay, so I'm hoping everyone is sitting there with the latest version of SDSM. As I said, December 2015, a new one will be coming along soon, and it will work perfectly with the procedures that we're following today. But that's the version we're working with today, step 3. Step 4, if everyone can go to the main screen, and what we're going to do is now check the basic settings, and we'll do a few preliminary activities, and then we'll take a little break if you like, or we can just press on to lunch. If you'd like to click on settings, the settings button. Does everyone have SDSM up and running now? Can we just check that that's the case? Okay, are we in good shape? Yeah, all right. So if we click on the settings button, this is step 4 in your worksheet, and it's important to make sure that certain things are set up correctly here. I'm going to highlight 3 things, actually. So first thing is to make sure that the start and end dates match the predictor variable files. So check that you've got 1948 to 2017. It's 2017 because that's when our predictor variables run out. I mean, we need to update that to 2020 to match the years since, and so we won't be using any of the Novisad data beyond 2017 today. Okay, so check that you've got those dates. Because we're modeling temperature, we want the model to be able to create negative values as well as positive values. So make sure that that box is clicked. And then most importantly, make sure that SDSM can find your directory where you're holding the box data set. Okay, so this is the pathway to the predictors. Does that make sense? Again, if Bianya and Minucha can just check that everyone's got that pathway set up.
We're just finding the folder that needs to be clicked, so it's fine. We can. Yeah.
Does everyone have that set up, the correct pathway?
Yes. Now, yes.
And I want to just emphasize that your your pathway might be different to my pathway. You just pick a file structure that makes sense to you. Okay. All right. So let's assume we've done that. If you click on save, that will save the master settings. And then we can click on back and it will take us out of the software and back to the main screen. Okay. So it will take us, click on back, it's back to the main screen. And then in the main screen, if you click on quality control, you should see the screen that I'm showing now. Okay, is that good, everyone? Yep. Now, in quality control, please go to the, click on the select file button and then navigate to the Novi Tmax file. Okay, we'll just check that everyone can do that. Are we in good shape? Thumbs up. Yep. Okay. All right. So now if you click on check file, hopefully you will get the same results as I'm showing here. Let's just do that and check that everyone's getting the same numbers. Yeah. Is that good? Does everyone have the same numbers or do we have any problems?
It's all good. We can go on.
It's all good. Okay, so this is a really useful step for two reasons. One is it helps us to just double check the sense of the data, you know, to check the range as we've just done manually in Excel. And as I said, the next version will include petite tests, day of week tests, so extra information. But it's also helping us to check that the files are being read in correctly. Because if you don't get this answer, you're not. If you don't get any information like this, then your files aren't working properly. So it's a good check of the file systems. Okay. All right. Now then, let's move to the next step. Transform data. We're not going to do this today, but I just want to show you the screen. This is would be used, for example, if you wanted to convert your data into a normal distribution or some other distribution. You want to apply a transformation to the data set. Okay. Now then, this is the most important part of the whole downscaling process, and this is the bit where we decide which predictor variables to use to build our downscaling model. So if you move to the screen called Screen Variables, you should see something like this. Okay. Now, let's just check that everyone's got this. that good? Okay. Now, I'd like you, as before, I'd like you to open up your Novi temperature file. So you click on select predictant, open that file. Then you set the fit and end start date, 1961 to 1999 in here. Now, before we go any further, let me just ask you, why do you think I've chosen these dates, 61 to 99, when we've got data up until 2017? Any ideas?
The PD test is significant at that point.
Thank you. Perfect. Perfect answer. So this shows the power of linking the petite test to the downscaling, because if we fit the model on the first part of the record and then test it on the second part where we know there's a step change, that is a really, really tough test of the model. So if the model still works well for a period later on, we'll see, where we haven't calibrated the model, then we're really confident that it can capture the non-stationary climate conditions or the trends over Novi Sad. So it's a wonderful way of bringing the petite test in alongside to inform our calibration of the downscaling model. Okay, that's why we're integrating this in the next version of the software to help people do that. So 1961 to 99. And then you can click on the predictor variables, which you can see here. The software will allow you to select up to 12 variables at a time. Okay. It also allows you to select an auto-regressive term. So that's saying that the model temperature depends on the temperatures of the previous day. So you're building in some memory into the statistical model as well. And finally, we need to check that we've got an unconditional process. An unconditional process is one where we go directly from the large scale to the local scale. Large scale weather patterns to predict the local maximum temperatures. A conditional variable might be like rainfall, where we're going from large scale to the rainfall occurrence, which then conditions the rainfall amount. So we want to make sure that we have the unconditional button checked there. Finally, make sure that in this box that you've got the your predictor file set selected. So it's linked in there. Actually, having said that, we should have done that as the first step. Make sure you can find the box. Then that will reveal the list of predictor variables. This is a sort of a subtle thing in the model. So before we go any further, again, Biljana, Minuccia, if you could just go around and check that everyone can see the predictor variables in their files.
We have it all set.
Excellent. What a master class. You're doing really well so far, given that I'm thousands of miles away. Well done. Okay, so the next bit, once you've got it set up like that, if we click on the correlation button, it should produce a table like this. Again, if we can just confirm that everyone has got to that point, that would be really good. And then I'll explain to you what we're actually looking at here.
We all have the correlation, yes.
Excellent. So let me describe to you, explain to you what we've got here. Two sets of information. So at the top here, we've got essentially a correlation matrix. So it's all of the variables correlated against one another to show the interrelationships within the data set. So column 1 is our variable of interest, the maximum temperatures. And then if you look down column 1, you can see the strength of the correlation between the daily maximum temperature at Novi Sad and these large scale weather patterns, indices here. So the ones here, for example, I'm showing you on the screen shows a correlation of 0.765 between the maximum temperature and the amount of direct shortwave radiation. So that's wonderful. That's exactly what we'd hoped for, that on sunny days, days with intense sunshine, we have higher temperatures in Novi Sad. That makes sense to me. Here, the lift index is a simple measure of the kind of storminess, the potential for convection and convective rainfall. So when you've got a high chance of that, obviously you're going to have perhaps some big clouds that can give really intense storms, and so you'd expect perhaps lower temperatures on those days because it's cloudy, and that fits as well, and so forth. You can go down the list and you can see the relative strength. You can see, for example, P-V, which is the strength of the surface airflow from the south, doesn't seem to have much of an influence on Novi Sad. And I wonder whether that, if my geography is correct, is because you've got a mountain chain to the south of you. Is that right? There's some big mountains to the south of Novi Sad, and so maybe that hinders airflow from that direction, and so forth. The other piece of information here is the partial correlation. And that is showing you the unique bit of correlation that comes from each of these variables, because some of these variables are very closely related to one another. So there's an overlap in terms of the association. So if you remove the association between direct shortwave radiation and, for example, pressure, mean sea level pressure, which is MSLP, and all the other variables, you can see that the unique contribution to the overall correlation that comes from direct shortwave radiation, which is still very high compared with these other variables. But you can see the autoregressive term is super strong. That's exactly what you expect. The temperature today depends very much on the temperature yesterday, statistically. So that still emerges as a really strong predictor of the day-to-day temperature variation. And the final thing to note is this p-value. That's telling you the significance. So you can see that the P-F has a p-value of 0.297. So that would not pass the significance test, because if we set a threshold of 0.05 or more stringently at 0.01, that's an insignificant partial correlation. So straight away we can say that that variable is not giving us any useful information in this model. Okay, so there's a lot of information contained here. Some of you might be thinking, well, Rob, why didn't you just set this up as a stepwise multiple regression where it just goes through and it picks the best variables and tells you what the shortlist is without the user having to do this? But we've deliberately designed the software to make you look at the variables and to think about the physical sense. Can you explain why there's an association rather than just a statistical black box where we put all the ingredients in and remove remove predictor variables that do or don't work. So it compels the user to think about what's going on at the local site and to justify your choice of predictors based on physical reasoning. Okay. If you click on the back button now, you go back to the screen here. And if you then now just click on the scatter, if you unclick your variables and you just have one, let's unclick and leave just say the direct shortwave radiation by clicking on that, and at the bottom you should see the number of predictors selected is 1. You should also unclick the autoregressive term as well, because that counts as a variable as well. Okay, once you've done that, you can then click on the scatter button, and that will visually show you the relationship between the two variables. Liana, this might be a good point to check that everyone's got the same plot.
Yeah, I'm just going to check.
Okay. Okay, does everyone have the scatter plot?
Yes, yes, we managed to make it.
Excellent. That's really good.
Yeah.
Now, you're all set to begin to build your own model for maximum temperatures in Novi Sad. Okay. So what I'd like you to do is using the screen variables, you're going to now, for the next however long it takes you, build the best model you can for Novi Sad. And so here are the instructions that I'm going to leave with you. So work within screen variables, and I want you to try and find a small set of predictor variables that give the best overall explanatory power for maximum temperatures within Novi Sad. And I in step 2 of this, in number 2 of these instructions, I'm emphasizing you want to build a parsimonious model. So you don't want to throw everything into the model and overfit the model to the 61 to 99 period. So as a rule of thumb, I would be looking for between, let's say, 3 and 7 predictor variables to keep the model parsimonious but sufficiently versatile to reflect different conditions driving maximum temperatures in winter and summer, for example. You should decide in instruction 3 whether or not you want to keep the autoregressive term in your model, and you should decide which period of record you're going to build your model on. Now, I think Biljana's already given you the answer to this, that we're going to use 61 to 99 because the fatigue test tells us that would be a really smart thing to do. Okay, so you know the answer there. Just build your model on 61 to 99. As you're looking at different mixtures of predictor variables from the large set available to you, ensure that all the partial correlations are significant. So you don't want to include any variables that might seem to be strongly correlated, but could have a low partial correlation because their association is due to other variables in the mix. And then finally, use your local knowledge of the geography and the climate of Novi Sad to think, is my set of predictor variables sensible for this site? Okay, have I got variables in there which I can explain, I can justify why they're included based on primary reasoning, basic understanding of the climate controls of maximum temperatures. Okay. I'm going to give you a top tip as well before you, this is my final top tip. You'll see in the list of variables, temperature is provided from the large scale. You might be tempted to try and downscale local temperature from large scale temperature. But the large scale temperature from the reanalysis probably includes information from stations like Novi Sad. It's been assimilated into the reanalysis. So there's a danger here of double counting. You're using potentially information from Novi Sad that went into the predictor variables set to then simulate local temperatures at Novi Sad. So my top tip to you is build a model without the temperature predictor variable. That will exclude the possibility of any double counting in the modeling. Does that all make sense? That's your task list, and I think I see, according to my clock, there's about a quarter of an hour to go till lunch, and I suggest that you start playing with this until lunch. Then we'll come back after lunch and continue with this part of the exercise. Now you might be thinking, oh, Rob, I've only got to step 8 out of 20. When is this going to end? But actually, this is the most important part of the downscaling process. Once you've decided on your predictor variable set, calibrated the model, all the other steps just take a few minutes to complete. So we're going to concentrate our effort for the next chunk of time on building the best model we can. And my challenge is, can you find a mix of predictor variables that will beat the professor's mix of predictor variables? Okay. I'd like to think I'm a humble man, and that somewhere in that group there is going to be someone who can do better than me.
We can continue.
Okay, are you ready to proceed to the next step, do you think?
Yes, we're ready.
Okay, good. So if everyone in the room would like to write down their favorite set of predictor variables, let's compare what you came up with what I came up with. And I'd like you to stick with your preferred choice as we move through the next steps of the model building, because I'm interested to see how different solutions might play out in the next steps. Okay, so these are the ones that I came up with. Let me just click on this. There we go. So I've chosen 5 predictor variables, which include the direct shortwave radiation, because that gives us a good sense of the energy balance affecting the temperatures. Mean sea level pressure, because that describes possible subsidence of the atmosphere and blocking weather patterns that tend to exist during heat waves. I've chosen the PU variable, which is the west to east airflow. So that represents potentially advected heat, west or east to the site. And then I've chosen the geopotential height at the 850 hectopascal level, which again is a good indicator of tropospheric heat and of blocking. And finally, I've chosen the lag1 autocorrelation, the autoregressive term, because we know that the temperature from one day to the next depends on what happens the day before. I've calibrated my model on 61 to 99, as we talked about before, because of the petite test breakpoint. And now I'm going to compare how well my model performs for this second period, which is outside of the training set. So that's what I came up with. And to be honest, I didn't really spend that much time working on this, probably half an hour at most to arrive at this set. So similar to you. And I'm just wondering now, what, if any, other variables people uncovered in the room that they think might be included in this model? I'm just interested to hear. So any thoughts? Either please put that in the chat box, or just unmute your microphone.
If nobody will, I will see what I chose. I chose direct solar shortwave radiation.
Yes.
Mean sea level pressure.
Yes.
Geopotential height. Let me see where it is. Geopotential height at 500 hectopascals and also at 850. And also relative humidity. I chose relative humidity at those heights also.
Okay, now relative humidity, I thought about including that as well, because relative humidity can be a useful indicator of the likelihood of cloudiness, so the amount of cloud cover, which might affect the highest temperatures at different times of the year. So again, we can argue the sense of the variables you've chosen, but if you'd like to hang on to those and then use those as we go to the following steps, it'd be interesting to compare the results.
I will.
All right. So this is what my correlation matrix looked like for the 5 predictor variables. So you can see that they're all strongly correlated, and the partial correlation statistic shows that they are all statistically significant. So I've got a small number of predictor variables that are contributing unique information and are all well correlated with the maximum daily temperature. So I'm confident that I've got a sensible set of variables to work with. There is an addition function within the model building screen, which is to analyze the results. Now, we're aware of a bug in the software at the moment. It works sometimes, sometimes it doesn't, but when it's working, and we're going to fix this in the next version, it shows the strength of the regression on a month-by-month basis. So you can see which predictor variables are strongest at which time of the year. So you can see from the results here that the temporal autocorrelation of the data set reaches a maximum in the late winter and spring, and a minimum in the late summer and autumn, whereas the relationship with the direct solar radiation reaches a peak at the end of the summer. So this is quite an interesting facility, a diagnostic, to explore the variations within seasons in the strength of different predictor variables, which can also inform your choice, because we've built the model on the year as a whole, but we could have tried to calibrate the model focusing just on the summer months, and we might have arrived at a different set of predictor variables had we narrowed the focus. So I just raised that for information. I'm not going to dwell on step 9, because this applies to rainfall modeling, where we have to apply some additional transformations to enable the simulation to work, to fit to different distributions of rainfall amounts around the world. So if you want to learn about rainfall downscaling, please show up to the next workshop in November, where we'll be continuing this journey. Now, we're ready to actually calibrate the model using our selected predictor variables. So if you'd like to move to the calibrate model page of the tool, and make sure that you have again selected the predictand file, the temperature data. Once you've done that, please then click on the output file and give that file a sensible name. And this is where you're going to be storing the PAR file. So remember, before lunch I mentioned this is the file that stores all the model parameters and is the way in which I can quickly diagnose any problem with your model setup. So if you do that, and you then also set the data period to 1961 to 1999, that's which we're going to use for calibrating the model. And then go through the list, and having found the box containing the predictor variables, then select your preferred variables. make sure that the monthly button is pressed here. If you want to include an auto-regressive term, that memory effect, then please click that. And then the last two things to settle on are the child test, which when we fit the model helps to test the stability of the model, and also click on the cross validation and put five folds in here. This is just building the model on 5 little independent blocks of data within the record you've chosen to see how well it performs, even within the training data set. So I'll just give you a minute or two to do that, and then Liliana and Minuccia, if you could just walk around the room and check that everyone's set this up nicely, then we're ready to calibrate. Thank you.
All set.
That's good. Excellent. All right, so we're all set. Now if you just click on the calibrate button, hopefully it will go through all the steps and will tell you when the process is over. So that if you just do that as the next step and confirm that that's all worked for everyone. You should then see a screen, something like this, once you've clicked the calibrate. Okay, does everyone have that? Hopefully everyone has that. Now let me explain to you what we're seeing here. So this is a summary of the calibration fit of the model. So you can see the list of my 5 predictor variables first. Then we can look down the month by month, the amount of explained variance in the maximum temperatures on a month by month basis. So overall, during calibration, my model explains 83% of the variance. So I'm pretty happy with that. That's a pretty good model fit. But maybe some of you have got a higher amount of explained variance than that, and that's even better. Then we've got the standard error of the model in degrees Celsius. So you can see on most months, the standard error is about 2 degrees Celsius. So that's the standard error in the model estimate. And then we have these 2 tests, the Durbin-Watson and the child test. So Durbin-Watson is checking to see that there's no autocorrelation left in the model residuals. So we're hoping for a number that is close to 2 here. And we can see that most of my months have a value close to 2. There's a slight positive autocorrelation in here, but it's not statistically significant. And then this last column here, the Chow test, is looking for any breakpoints in the data. Now that's showing that despite the fact that we applied the Petit test, there are still possible breakpoints, non-stationarities within some of the months here highlighted in red. And that's something to keep in mind if and when we go into a more detailed analysis of the model performance, but we'll just park that for the time being. And then this final block of results is just showing the cross-validation performance and the bias of the model, which is pretty small. So we've got here with these 5 variables, a good fit to the data and a good overall performance. Has everyone got a similar screen to that? Can we just confirm that before we move on? Okay, everyone's good. Yep, okay. So if you click on the back button, that'll take you to the master screen again. And now we need to move to the next step in the workflow, which is the weather generator, where we're going to now simulate the full period of record with our model. So what you need to do is click on the select parameter button and select your PAR file that you've just created, and then make sure that you've opened the box again containing the predictor variables, and to confirm that the model is set up ready to go. If you click on view details, it should confirm the choice of predictor variables, the number of predictors, and whether or not you have an autoregressive model. So if you can just do that, I'll give you a minute or two, and then if Biljana or someone can confirm that everyone's good, we'll proceed. Those of you who have are happy with what you've got here, then just make sure that you've got the start date set to 1st of January 1948 with a synthesis length of 25,568, and that's the full record of the data. And then finally, click on the Save Output File button here and enter a name and for the file. And this is the file that's going to contain all the downscale model results that we'll be analyzing next.
Rob, excuse me, this place where you put synthesis start, it should be 48, even though the data are from 61.
Yeah, it should be 1948 because okay, the predictor variables from the reanalysis, that's when they begin. And as I'm going to show in a minute, with this, we can actually reconstruct what the temperatures were for Novi Sad before 1961. So I'm going to be giving you some data.
Okay, thank you. Now I understand. Thank you.
Thanks for the question. Okay, and if everyone is happy with this setup and it looks something like my screen here, if you then click on the synthesize button, you should see a sort of a blue bar moving across the screen as the software does all the number crunching. you should then get a message that says that the simulation, the weather generation is complete. Has everyone managed to do that?
I think, yes.
That's great. I'm amazed how well you're doing remotely. Yeah, well done, everyone. Okay.
If project officer sees how good we are doing, then the travels will be banned forever.
Okay, excellent. Now then, so we've actually created a big ASCII file full of results from your calibrated model, and it provides a simulation of daily maximum temperatures from 1948 to 2017, even though we only gave the model information from observations between 61 and 99. So it's simulated the period before and the period after, and we're going to be exploring the data shortly. Some of you might be wondering why we've got this 20 here. That represents the ensemble size. So if you look at, if you were to open your output file, which is just a text file, you'd see 20 columns. So each one is the full time series, but run 20 times, because there's a stochastic part to the model that is used to simulate the residuals of the regression model. So that's all provided, and so you've got 20 columns of output, each of which should have the same mean and variance, but slightly different day-to-day values. So that gives you a way of exploring the uncertainty in the downscaled results. So let me just now illustrate how my model performed before I set you the next task. So when I ran my weather generator, remember we fit the model on 61 to 99. So if we look at any results outside of that period, that's a really tough test, because it's simulating a period for which we hadn't calibrated the model. So I chose 2013 because you remember that's the year where we had the missing value. So what we've got here is the black line shows the observed temperature in 2013. The red line shows SCSM, what it produced from the simulation, from the 5 variables that I gave it. So I'm pretty happy with that, given that this data hadn't been seen before by the model. And it gives me a really nice representation of the warm spells and the ups and downs from day to day. And if I go and look at the my value for 31st of October 2013, it tells me that the model thinks it should be 16.9 Celsius on that day, plus or minus 2 degrees, which is the standard error of the model estimate. And if I'd applied a conventional interpolation method between the day before and the day after to estimate what the missing value was, I'd have a value of about 9.6. So there's a bit of a difference there, although they're probably not statistically significant because of the uncertainty in the model simulation. But it just illustrates how we can use this tool to repair or infill missing values. And then finally, I looked at how well did the model perform during the 2007 heat wave. And again, remember, this is simulating information outside of the calibration set, and it's simulating for an extreme event. So this is a very, very severe test of the model, especially as we know from the petite test that there's been a step change, a regime shift in the temperatures with it at Novi. And yet, again, the model during that summer is doing a pretty good job at capturing the various heat waves that we're seeing here and the warmest episode, although it does actually underestimate the peak temperature on this given day. Now, we could speculate all sorts of reasons for that. Maybe we need to include some extra predictor variables or change the predictor variables. Maybe there was something special about the weather on that day. I don't know, but it allows us to sort of go into the information a bit in more depth to try and understand what the model's doing. But overall, I'm pretty happy with how that model performs, especially when I look at a time series like that. I'm happy that it's working well, even after half an hour of effort to fit the model. So now the task I'd like to set you is you use the weather generator. So you've done that. You've created your output, and you've got now daily data for that full period, 1948 to 2017. I'd like you to read the data in your out file into Excel, and I'd like you to just quickly try and extract the information for year 2013. So you might have to create an extra column with the dates, dragged all the way down to the bottom to find the year. And then let's, as a group, see what your estimate is for that missing value on the 31st of October 2013. And if you have time, let's see what your maximum temperature plot for summer 2007 looks like.
Rob, I'm sorry, are you there?
Yeah, I'm here.
When we finish the synthesis and put everything in the Excel file, what values do we take? Do we take the mean of those 20 samples, or we choose the column we would like?
Now that's a great question. So, so you've got 20 columns to choose from, haven't you?
Yes.
Okay, so what I do is I like to use the ensemble median. So you can use the percentile command or the median command in Excel and find that. I mean, maybe do this another time. My main intention here was that people were confident that they could read the information into Excel and post-process it in different ways. You can plot and analyze it, but you see, I hadn't actually, whoops, here in this plot I'm showing on your screen now, and the one before it, that represents the ensemble median.
Oh yeah, sorry, I didn't
No,
pay attention to that.
That was my fault. I didn't explain it, and I could have shown the upper and lower bounds of the ensemble as extra lines on the graph, or as an envelope of uncertainty. If I was super rigorous, that would have been a good thing to do. So thanks for raising that. If you've been able to find the row with for the day 31st of October 2013, what kinds of values have people been able to get?
I'm just looking. Just a second, please. 31st of October. It's I need to take the ensemble median, and then I'll tell you.
Okay.
I didn't finish everything. It's between 21 and 15, or maybe even less. I'll just just take me a little bit more time.
That's all right. So the main point is that you've got a model and it's coming out with values that are similar to mine, that you'll be able to calculate the median, the best estimate for that missing value, and that you can attach a confidence interval to it from the output. Okay?
Okay.
All right, that's very good. Now, what I'd like to do is just again sort of move on, and we'll be able to analyze shortly. Okay, we've got a question here. Thank you. Median 18.59. Okay, very good. So that's actually that's interesting, because your median has come out closer to the estimate I would get with the interpolation. So Igor, what predictor variables did you use in your model? If you're able, just type them in the box, and that would be great.
Type them in the box.
Okay, so while Igor's doing that, let's move on to the next step.
Okay. My median is 18.5.
Okay, so it sounds like the guys in the room are getting a warmer reconstruction than I did, which is fine. But I think I really want to highlight the power of this tool for repairing and filling in missing data, and also for extending backwards in time to periods where you might not have any data. And we can demonstrate that shortly. Thank you, Igor. So direct shortwave solar radiation, mean sea level pressure, and the two geopotential heights. That's interesting. Okay, thank you. Right, let's move on to the next bit. So if you'd like to go back now to the main screen and select summary statistics, this is where we're now in the part of the software which gives you lots of diagnostic tools for exploring the results from your weather generator file. So what you need to do is to go to your input file, which is the weather generator, the .out file that you created in the last step. Select that. Now enter in a file name that makes sense to you, that will contain the summary statistics. That can be anything you like, but something that makes sense to you. And most importantly for today's exercise, put the period 2000 to 2017 in this in these boxes here, because this will allow us to explore the results for the period that wasn't used in the model calibration. Once you've done that, can you please then make sure you've clicked on modeled output, and then you can click on view details. That will then confirm that you've got the right file, you've got the right number of predictors, the right period of scenario, the right number of ensemble members, and so forth. Then if you click on the statistics button, it will take you to this screen where you've got lots of ready-made statistics that you can choose from. And I've just, for example, showing you the 8 that I would use. So for simplicity and for graphing, the software only allows you to select 8 diagnostics at a time. So I've selected the mean, the maximum, the minimum, the variance, peaks over threshold, so that's counting the number of days greater than 30 degrees Celsius, the 95th percentile, the autocorrelation coefficient, and the maximum total for 5 days. So that's giving a summation of the temperatures accumulated over the hottest 5 days in each year or period of analysis. Okay, so when you've done that, you click on the back button and it takes you back to the screen, and you can then click on the analyze button and it will produce some statistics for you. Okay. If you do that, you should, if it all works, end up with a screen looking like this. I'll just give you a minute or two to check that that's the case for everyone. And Biljana, if you could confirm that everyone in the room is in the same place, that'd be great.
We are all set.
Everyone's good? Okay.
Yes.
Excellent. There's no need for me to be there, is there?
No,
really?
no. We need you here. Thank you.
Okay, so we've got, let me just explain the results here. For each month and each season, and for the year as a whole, we've got the mean, the maximum, the minimum variance, peaks over threshold, percentile, autocorrelation, and maximum 5-day totals in this block of results. And then underneath, we've got the standard deviation in the results, because we've got an ensemble of 20 members. So you've got 20 values to calculate each one of these, 20 columns to calculate each one of these diagnostics. Okay, so that's really good. Now, if you go again back to the main screen, now I'd like you to click on the observed button and select, this time select the observed data. Remember, that's the Novi maximum temperature OBS file that we've been working with all along. Click on the Save Statistics button and give that another name that makes sense to you. And also double check that, again, we've still got the 2000 to 2017 window that we're analyzing. Okay, and when you've done all of that, you can, again, it remembers the statistics that you used last time. You can straight away click on the Analyze button, and you should get a similar screen to this one, but with no standard deviation results, because you've only got an ensemble of one, because there's only one reality. So they tell me. Okay. Has everyone got that? Yeah, Biljana, again, if you can confirm that you got the results.
Yes.
That's great. That's really good. Now the really exciting bit, when we get to compare the model with the observed results. And we do that in this screen called Compare Results. So if you click on that, you might use the back button a couple of times to get to the master screen. Click on Compare Results. Then you just select for your first file, the file containing the statistics for your observed data. And then so that for the second file, the one that contains the statistics from your weather generator. Once you've done that, then you can quickly graphically compare the observed diagnostics with the modeled diagnostics for your 4 chosen statistics. You might compare mean with mean, or variance with variance, or here I'm going to show you comparison of the autocorrelation function. I think, is that right? Yeah, I think that's the autocorrelation. Yeah, that's the autocorrelation between the observed and the weather generator results. Does everyone get something like this? if you're able to confirm in the room that we're okay, that we're getting plots like this. I'm hoping that as you compare your observed with the mean, with the modeled results, you're getting a nice fit between the two.
Yes, most of the group has got good results. So there are some minor problems, but I think the majority did well.
So, are they the problems that you have with using the software, or the comparison of the results show quite big differences between the observed and the modelled? What's for those who haven't got very good results? What's going on in the room? Can you tell me?
I think that almost everyone has similar results. The problem is that actually in saving the document, that there was a problem, because they saved it under the same name, so that's the problem. So
okay, so in which case you just go back a few steps and regenerate the file, and then all is good. Okay. All right, so in the interest of time, I'm going to sort of speed through the next few bits, and then we'll take a break. How does that sound? Okay, so
yeah, that's fine.
All right, so with these screens, these just don't look very nice at all. So you can use the settings button to customize the presentation. So, for example, and I'm going to skip this exercise because you've already done that. Here I've customized the output to compare the absolute maximum from my model in the red with the absolute maximum in the observed data. And you can see I've changed the label, I've changed the ticks and things like that, changed the labeling here just to make it look a bit tidier if I was to use this in a talk or a presentation. But of course you could output the information and plot it in Excel if you prefer, or some other drawing package. Here's a result, which is a very, very tough test of the model, comparing the peaks over thresholds. So here I'm seeing that SGSM slightly underestimates the frequency of very hot days in these 2 months, in June and I think it's June and July. Okay, so that again gives us, maybe this is okay. If I plotted the confidence intervals around this, maybe the observed data lie within the confidence intervals of the model. So that's again something that might prompt deeper investigation. Then I'm just, in the interest of time, we're not going to do this, but I want to just show that there's the ability to do frequency analysis for looking at extreme values. And this allows you to do quantile plots, comparing extremes, comparing the distributions of the observed, shown in the black, and the red is the SGSM. So you can see that this simple model for this period 2000 to 2017 is doing a nice job at simulating the overall distribution of the daily maximum temperatures. And for rainfall estimates, you might be interested in seeing what the extreme value is of over different return periods, and you can fit different distributions within the model to that. So what is the 1 in 100 year rainfall amount? This isn't for Novi, this is for another site. You can do that too. So one last exercise then before we take the break. And that is for you to do the time series plots. So that's the very last button on the master screen. And what I'd like you to do is to set your screen up in this way, where you select the time period is summer. You select your observed data file, the observed data set that I gave you at the start, and you select the file containing the output from your weather generator. So just those two files. You might need to navigate between these folders till you get to the right place, wherever you put that information. And then I'd like you to set the date range from 1948 to 2017. And let me see, let's pick the mean. You've got lots of diagnostic tests here. Some of them only apply to rainfall. Quite a few of them actually only apply to rainfall. But we're just going to produce two time series of the annual mean summer maximum temperature series for the observed and the downscaled results. So again, once everyone's set that up, could someone in the room let me know you're ready to go? Are we in good shape? Are we ready to go to the next step?
Rob, could you please repeat to us which files should we select? Because I'm struggling as well as others to find.
Yeah, you might need to. I tell you what, if you just sort of click back along a few buttons, it might refresh the pathways to your folder containing the results. So if you just, click.
Yeah, now I see it. Yes, thank you.
Okay. Yeah, again, that's a. Yeah. Is it?
Ovaj ops, znači sve prvi, da.
Okay. Is it?
Sorry, on the left-hand side, the one that we should select is the first file that we use, that observed.
Yes, and then the one that you created from using your weather generator.
Okay, that's the extension out.
The dot out. That's the one. Yeah.
Okay, thank you.
Yeah, there is a little bug in the software and it forgets the pathway. So that's on my list for Chris to fix.
Okay.
All right, when you've done that, you plot it. You should hopefully get a result like this.
Plot, okay.
Yeah, if you click on plot, do you get something like that?
I think that the problem will be that I did not select only one column in that dot out file. So yeah.
It might say something to you like there's 20 ensembles.
Yeah, that's saying.
And just ignore that message. It's just a little warning to say that it's only going to pick one of the ensemble members to plot.
Okay. It says that warning, and now it's generating time series. I'm just.
Yeah, you might see hopefully a little blue bar moving across as it processes the data. Does it work?
Yeah, it works.
Excellent. So this is where I was when I got these results, I was really excited because here you can see, remember, we calibrated the model on the period 1961 to 99. So this block of information here, and the fit isn't that great during the calibration period, but it works really well in the test period here. Very good results. And the other thing that those of you who are interested in long-term environmental modeling, you've now got a maximum temperature series for Novi that begins in 1948 that goes right through to the present. So you've reconstructed that there was this warm period in the late 1940s and 1950s, and then like in the UK, you've got this cool period in the 1970s, and then much warmer conditions ever since. So you could use this information in all sorts of ways for different types of impact modeling or plotting changes in the environment through time. Okay, any questions from this so far?
No questions in the chat.
Okay, all right. I'm conscious that I've been making you work very hard for a long time. So, and you've already accomplished step 5, so that's good. The remaining steps we're not going to do today. This is for looking into the future, producing a future scenario. We don't have time to do that today, but we will be picking that up at the next workshop. So I hope that everyone feels satisfied that they've learned the essence of how the model works, how it's set up and how it's built. To apply it to the future climate conditions, you use the scenario generator, and there are choices to be made there. And if you go to the SGSM website, you'll find a supporting technical document that explains to you step by step how to produce the change climate scenarios. And these can be used in all sorts of ways to test how, say, a hydrological system or a water supply system might behave in the future with this kind of information that you can take from your output file. On the SGSM website, we've also left version 4 of the software, which actually uses climate model output to drive those future conditions. So this version of the model is a weather generator where you can adjust the weather generator parameters to produce hypothetical climate conditions, whereas the traditional version of the model takes climate model information to drive the future conditions, and that allows you to produce conventional climate change analyses. Here, for example, is some results that I produced for Syria before the present conflict. We were working on supporting the agricultural sector there, and you can see, for particular locations, how the temperature or rainfall might change at different periods in the future. That's a sort of a very traditional way of using the downscaling models, but it's a way that I'm less enthusiastic about now. I think it's much more helpful to use the model to evaluate decisions in a stress testing situation. And after the break, what I'd like to do is give you a case study of how we did that in practice. So if that's all right with everyone, let's take a break now for 15 minutes. Come back at, what is it, 3 o'clock your time. I'll adjust the schedule slightly, so I'll give you a shorter demonstration of how we use SDSM in a stress testing application, and then we'll finish off with the quiz and any last minute questions and answers. How does that sound? Is that good?
Yeah, this sounds nice. Yes.
All right. Okay. Everyone's been doing really well, so enjoy your coffee and let's meet back at 3 o'clock.
Yeah. See you.
Okay. In a minute's time.
Yes, we are ready to continue.
That's great. Now I'm going to, in the interest of time, so we finish in about an hour, I'm going to keep this primer talk short. We'll do the quiz, and then we'll have a few minutes at the end for any last minute questions and answers and next steps. How does that sound? Okay.
Yes,
right.
yes, we are okay.
Okay, that's good then. So what I like to do now is just give you some examples of how SDSM can be used, the kinds of application, but also not how it might be used in different ways, but the type of framework that we implement downscaling within, and hopefully I will explain that in a little bit more detail. So I'd suggest that, excuse me, I'll just move the slide along, that up until relatively recently, much of the climate modeling community has put the cart in front of the horse. So we've been focusing much of our effort on the climate scenarios and less of our effort and attention on the actual purpose of all of this, which is ultimately to support decision making. So my argument is that the downscaling tools like SDSM should be used to support decision making, but we shouldn't be concentrating all of our effort necessarily on the scenarios themselves. And I'll explain what I mean by that in a minute. So the conventional approach of downscaling and scenario analysis is this so-called top-down framework where we think about the future scenario, the greenhouse gas emissions, the choice of climate model, the downscaling method, which then feeds information into an impact model. And then at the very end, we start to think about how we're going to adapt to those projected changes. And as this graphic illustrates, the uncertainty is growing at each step in this uncertainty cascade, to the point that when we get to the end and we're thinking about what to do, the range of uncertainty is so huge that it almost confounds us. We wonder, what can we do to adapt to so much uncertainty in climate change? And this really came home to me in a project I was involved in about 10 years ago in Tajikistan, where we were trying to model a future climate scenario, and from that changes in the snow and the ice, and from that changes in river flow into hydropower schemes, and then ultimately to think about how the hydropower production might change into the future. And when we applied that approach, we got just hugely different results depending on the assumptions about the future climate, the behavior of the glaciers, and everything like that. So huge uncertainty. And this is actually a very common result from this sort of top-down approach, that when we're really rigorous and we include lots of scenarios and lots of models, we get very big uncertainty in the projected future. And the way in which decision makers have typically dealt with that huge uncertainty in the future is to develop what I call low regret adaptations. So these are measures that you might implement to safeguard, in this case, hydropower production, regardless of the climate change scenario. And again, if you click on this link, it takes you to this very nice little report in which the European Bank for Reconstruction and Development went through these steps, analyzed the scenarios, looked at the impacts, and then they came up with these 3 scenarios, 3 different ways in which they might upgrade this aging hydropower plant to improve its efficiency and also to protect electricity supplies regardless of climate change. We haven't got time to go into detail today, but if you look at these 3 scenarios, each one of them makes sense. It's a good investment decision regardless of what the climate does. And that's an example of the sort of investment or change in asset that you can make even when you've got huge uncertainty about climate change. So that's the conventional way of using a downscaling tool. Now I'm saying that, and in fact, it was this work in Tajikistan that convinced me that there might be a different way of going about this. The real on-the-ground experience taught me or challenged me to think, well, is there another way in which we can use downscaling to help decision makers? And through experience came up with a framework which might be regarded as a bottom-up one, where you start with the vulnerability of the system now and think about the adaptations that you might implement. And then much later on, you use the climate model information to see which of those decisions performs better than others. So you're using the downscaling system as a way of exploring the performance of your decisions under a wide range of credible future climate conditions. So you're not trying to predict, then act. You're trying to explore the strengths and weaknesses of different adaptation decisions in the face of a wide range of climate conditions that might be generated by your downscaling tool. And in a paper a short while afterwards, we looked at how, for example, the water supply to the metro area of Massachusetts might vary in the future under changes in the mean inflow and changes in the variability of the flow. And these colored lines show the reliability of that water supply system from 95% through to a poor case of 30%. And each of the dots on this surface essentially represent a different climate future, which was downscaled or came directly from a climate model. So there's a huge cloud of uncertainty. But you can see some scenarios, some combinations of changes in the annual mean and the variability that cause real problems to this water supply system. So this particular scenario here, circled in red, is the one which would really cause difficulty. And so you can then begin to think, okay, what changes would I need to make to my infrastructure or my operations to cope with a future like this? It inverts the thinking. We're saying we're now being challenged to think about, what would I need to do to protect my water supply in the face of this kind of future? And that essentially, those experiences, this is the work with Casey Brown, who came up with roughly the same idea on the other side of the Atlantic in North America as I was thinking about this as well. And so we came together and thought, yeah, this is a nice way to go. And in fact, Casey Brown helped with the conceptual design of the new version of SDSM, which puts decision-centric at its heart. It's focusing not on the scenarios, but focusing on the use of scenarios to stress test systems and to evaluate decisions. But that's just one example of how this tool might be used. I'm going to give you 5 or 6 more, and then we'll go into the quiz, just to give you a sense of what can be done. So of course, example 1, we can use the tool like any other downscaling model to produce risk indicators. In here, for example, we're looking at changes in I think it was accumulated degree days through time, which could be important for crop development, in this case for the flowering of olives in Tunisia. And we can see the range of uncertainty in these projected dates of flowering. So earlier dates, later dates. This is the range, the dotted line at the top of the historic flowering date. And you can see that all of these scenarios suggest earlier flowering and fruiting of this crop. So at a qualitative level, this sort of analysis says that the timing of your crop, your harvest, could change in the future. So what are you going to do to manage that? You know, what are the implications for harvesting, packaging, transporting, selling, you know, moving your produce to market? So it just helps you think through all of those sorts of things using this sort of risk indicator. The second example is like the one we've done today. We can use the downscaling tool to fill in missing data. As I've shown you, I think already a plot like this for Tunis, where the dark black line represents the observed data and the grey line represents SDSM's infilling capability. So it allows us to repair, infill, and even extend way back in time, in this case to 1948 if we want, these long-term records. That's a powerful function. I've shown also earlier today that we can model different types of variable that might not come from immediately from a climate model or a regional climate model. And here I'm showing examples of simulations of storm surges, extra heights of water in the Thames estuary associated with low pressure systems moving around the North Sea. We can use the model to simulate the very nicely the return period and magnitude of the skew surge in the Thames estuary, and you can see the model does a very good job at representing the historic distribution. Like the example I showed you for Massachusetts, we can use the output from the model to test the effectiveness of an adaptation decision, such as in this case, would a 20% allowance on a flood defense be good enough to protect against future floods, future changes in rainfall, seasonality and extremes? And so again, like the previous example for Massachusetts, each dot represents a possible future from a climate model. And when the dots fall on the left of the line, the red line, the 20% allowance is good enough to protect us against climate change. But when it falls from the right, there are some models where the change or the scenario that has been downscaled would exceed the standard of protection for this flood defense. So it helps a decision maker or an engineer to decide whether or not they have sufficient margins of protection built into their infrastructure to cope with future changes in climate. And this is an increasingly common use of this sort of tool. This is a really complicated diagram, and one for those who are interested in regional climate model simulation using models like WRF. And in this paper, which I mentioned earlier today, we compared the performance of WRF with SDSM at simulating extreme rainfall events across many sites in Spain. And it shows the extent to which a simple statistical model can perform as well as, if not better than, a very sophisticated dynamical model. So you might like to explore that paper again. If you click on the link, shows the relative performance of those two models, and that just came out a year or so ago. And then finally, I mentioned that you can use the modeling. The next version of SDSM will have this time scaling capability, which will allow the simulation of sub-daily rainfall extremes from daily records. So for many parts of the world, there just aren't sub-daily rainfall records, and yet using known scaling relationships in space and time, for example, we can see where we do have sub-daily rainfall, that there's a very strong, almost linear relationship between the duration of a storm and the intensity of a storm. And we can exploit that simple rule, which we see all over the world. We can exploit rules like that to estimate if we've got, say, a daily rainfall amount, we can 24 hours, we can estimate what the intensity would be at much shorter durations. And the graphs on the right show how well this works compared with observations in Uganda, where the purple bars represent records published by an engineer back in the 1950s. The black represents more recent data, and the red bars represent what SDSM predicts would be the intensity for a 1 hour duration event or 3 hour duration event with, say, 10 or 20 year return period. And you can see, by and large, the downscaling models doing a great job at estimating these hourly and 3 hourly intensities when only given daily information. So this is a new area which we're still developing. We haven't published this paper yet, but I'm happy to share the manuscript with anyone who's interested in this new frontier for downscaling, which is in sub-daily extreme estimation. Now, finally, we've got this detailed case study, and because we haven't really got time to unpack that today, I suggest you go to the reading, which is one of the 4 readings in the shared folder. So if you see the Yates paper, that will give you a really nice case study of how the downscaling can be used to evaluate an actual adaptation measure. In this case, it was Denver Water thinking about what steps can the company take to protect water supplies in the event of a drought. And we used SDSM to evaluate different conditions in the catchment and to examine how well their proposed solution would actually work. And I won't give away the end of the story by telling you the answer now, but if you read the paper, it gives you a really nice illustration of how you can use the tool in this new and I think much more exciting way than the classic predict and act approach. Now, I know that that's been a bit of a rush through. I'd just like to bring that through to some concluding remarks here before we go to the little quiz and have an open discussion. So what I've tried to show you throughout today is that the whole history of downscaling really began with a focus on the scenarios themselves, this top-down view. And now some of us, but not all of us in the downscaling community, are thinking about how we can use these tools in ways that are more helpful, more informative to actual decisions, to move the focus away from the creation of just more climate change scenarios to actually using this information to evaluate hard decisions and the behavior of systems on the ground, how they might behave in the future. And that comes under this broad set of approaches, which I've referred to as stress testing, where we're using the information from the downscaling not to predict the future and act on it, but rather to take a system with and without adaptation and apply these scenarios to them to see how the system performs with and without adaptation, to see which adaptation measure performs the best. And that's essentially the heart of the Colorado case study, which I'm encouraging you to read. And the final remark you might think is a bit of a strange one. We've all spent a whole day of our lives today looking at downscaling, learning how to do downscaling. And I'm summing up by saying, you know, downscaling is not always the right tool. So the top tip here is to think, what are you trying to achieve in your scenario analysis or your local analysis? If you're wanting to repair or extend a data set, undertake some risk analyses at local scales, or stress test an adaptation decision, then I think a tool like SDSM is very helpful. So you know, make sure you're choosing the right tool for the right job. And tomorrow and the rest of this course, you'll be hearing about other tools which may actually be more appropriate for your particular research questions or applications. So, you know, if nothing else sticks in your mind, remember my toolbox that, you know, I might think of statistical downscaling as a hammer. It's a pretty handy tool for putting nails in the wall, but it's not very handy for cutting a piece of wood. You might think of a regional climate model as a power tool because it requires much more computing power and capacity to apply it. But I wouldn't use a power tool like a drill to put in a nail in a wall. So it's choosing the right tool for the right climate questions that you might have in mind. So at that point, Liliana, I'll just pause there and see if there are any questions from the floor, and then maybe we can just finish on the quiz to see how people have how much people have understood today.
There aren't any questions in the chat, so maybe we can wait a minute or two.
Okay, well, if you'd like to think of any questions, what I'll do is I'll just switch to the quiz, and then we'll proceed with that, and then we'll just have a few minutes at the end to just share some thoughts. Okay?
Yeah, that's a good idea.
Okay, all right. Right. Hopefully you can all see the slide here, which is a view of the across the fields to the village in which I'm speaking to you from. So you can see why the internet is sometimes a bit of a struggle. Okay, so you know I like to end the day with a quiz. It's a way of seeing how much you've understood, and also hopefully a little bit of fun. I've got 5 questions for you. Let's see how you get on. So question 1 then. The most important steps when developing a statistical downscaling model are input data quality assurance checks, predictor variable selection, cross-validation of model performance outside the training set, or all of the above. So I give you 30 seconds to think about that. You can chat with your neighbour if you like. Please do confer. And then please don't be shy. Just turn your microphone on, or someone just tell me on behalf of the group which you think is the correct answer. Liliana, perhaps if you could do that for the folk in the room.
We're just discussing, but we're discussing in Serbian, so.
No, that's all right. Just let's keep the microphone open, and it'll make it easy. But yeah, by all means, yeah, please do discuss in Serbian.
Treće je da uradiš validaciju, odnosno, kako se to kaže, testiraš podatke koji se dobiju modelom na podatke koji su koji su izmereni. Stvarno izmereni, da. So we have one answer. It's from Tanya. It's D. Milica D. Rastko D. Everyone said D. All of
okay, and I think Tanya was first out of the blocks with answer D.
And she's not here. She's actually.
No, I can see Tanya here on the little screen. Okay. So the correct answer is D. Well done, everyone. Yeah. Okay, so I hope you've seen just from the little exercises we've been doing today how it's really important to check the quality of the data, spend time thinking about and justifying the predictor variables, and also thinking about a fair and tough test of the model. And that's where the petite test really helped us find a nice period to calibrate on and to test on to see if the model can capture the change between the 2 periods. So well done. So Tanya's on 1. I think everyone else in the room's on 1 as well. Let's see how you get on with question 2. Statistical downscaling should not be used for infilling and reconstructing missing weather data, simulating the strength of an urban heat island, modeling climate where there are major land use surface changes, any of the above. Okay, again, spend a minute or 2 just discussing and thinking about that one. It's quite a tricky question, this, because there's a few double negatives in there, and I struggle even in English. Okay, we got people coming in with answer C at the moment. That seems to be the most popular. All right, let's see. And the answer is C. Okay, that's good. I think everyone went with C. So we've seen today, of course, you can use this tool for infilling and reconstructing. I gave you a case study early in the morning showing how we can do this for modeling urban heat islands and even air quality. But we have to be careful in applying statistical downscaling where we know the land surface has changed, because things like soil moisture, vegetation, snow cover cause important feedback mechanisms that could change the local temperature or rainfall. And if that's the case, then we're much better off using a regional climate model like you're going to hear about tomorrow, where those land surface weather feedback mechanisms are incorporated in the model. So well done for everyone for spotting this. And actually, the case where I've come across this the most is trying to downscale temperatures in mountainous regions at the margin of the snow and the non-snow covered areas. So you can imagine if you calibrate an area that is without snow and then there's snow cover on it, that affects the thermal properties of the land surface and all sorts of other things. And so at that transition between snow cover and no snow cover, we can sometimes find some poor results from statistical downscaling because we don't have the land surface feedback. Okay, very good. Right, question 3. Which of the following statements is true? Downscaling always reduces uncertainty in local scenarios. Downscaling sub-daily rainfall intensity is impossible. Downscaling adds precision, but not always accuracy. Statistical downscaling always performs better than dynamical downscaling. I'll open the chat box to see what you're going to come up with. Tanya, straight out there with C. Everyone else C. Anyone not think it's C? Excellent. I think you're right. Downscaling adds precision, but not always accuracy. So just because we can simulate to a local position, like the meteorological station to the north of Novi Sad, doesn't mean to say that the results are necessarily going to always be accurate in a changed climate context, because as I talked about earlier today, what if changes in the aerosols are an important factor affecting temperatures, and what happens if air quality, those aerosols are cleaned up for sake of argument, then that if you haven't included that information in the model, then it might not work so well. It might not always be accurate, even if it's giving you a precise answer. Okay. Which of the following is a smart use of statistical downscaling? Predicting changes in highly localized rainfall extremes by the end of the century, stress testing water systems with and without adaptation, correcting highly biased output from global climate models, using only one climate model to downscale the future. Which of these is a smart way of using statistical downscaling? So I think we've got a highly autocorrelated system here. Whatever the first letter that goes into the chat box, everything else is correlated with it perfectly.
It was an error from my side. I was going to type B. So C is not present.
So someone was making a remark in the background. What was that?
Milutin told us that his initial C was actually a mistake. He was
okay. He just put that in to try and confuse everyone else. All right, so let's see what the answer is. Stress testing, okay. So I wouldn't go for A because A is so far in the future that how can we credibly say what the land surface will look like, the major weather patterns over an area could change so dramatically, the extent of an urban area could change, all sorts of factors could change that would influence the very localized phenomena. So A is problematic. C is problematic because if you're taking highly biased or erroneous information from a global climate model and downscaling it, you're back into that garbage in, garbage out situation. And lastly, I think we've all been trained to recognize that using a single climate model isn't the best way to go, because what happens if you've chosen a particularly hot, warm or dry climate model? We need to somehow capture the range of conditions in our downscaling. And then right before I was giving you this big hint that we can use these tools to stress test water systems and gave you the example. So well done, everyone was listening even at this stage of the day. Last question, and this is for the bonus point. Okay, so you get an extra point if you get this one right. SGSN-DC is an example of a regional climate model, a weather pattern model, a weather generator, or a conditional weather generator. So who was listening earlier today? Right. Okay, Tanya's going with D, Minuta's going with D. Anyone not think it's D? Wow, it sounds like this is the first quiz I've done where everyone's got 6 out of 5. Well done. Okay, so it's a conditional weather generator because the regression relationships that we've been building today for temperature are used to change the parameters of a weather generator that can simulate both temperature and rainfall and all sorts of other variables, whatever we want to calibrate the model against. Okay, so well done everyone. That looks like we got 5 out of 5 or more if you count the bonus point. So here's just some closing remarks and ideas. Before the break, I think I suggested that before we do any downscaling, we need to have a really clear idea in our minds what we're trying to achieve from this. You know, this takes quite a bit of effort and time to set up and implement. So what are we trying to achieve, and can we achieve the same result using a simpler or more effective tool? And by tomorrow, having gone through the regional climate modeling part of the workshop, you'll be in a much better position to judge whether the regional climate model is the tool for you or the statistical downscaling is better. So you'll have a better basis for that sort of consideration. I hope what you've seen today is, even with the little examples we've been working on, setting up a statistical downscaling model requires a lot of care in the calibration, the testing, and the choice of the predictive variables. And I think comparing that top-down and the bottom-up framework, it's really useful to think about how and when we use downscaling. Are we using it to predict and act, or are we using it, seeking to use it to test decisions? That's really an important difference. And now I didn't start off in this position, but now I believe that downscaling is not really intended for predicting the future. It's about generating credible information for testing decisions. So we're starting with the system of interest, might be the water resource system, the river catchment, the ecosystem. We're trying to understand what it's vulnerable to, and then we're using the downscaling to produce information to push that system in one direction or another using credible climate information that has been created by the weather generator. So I hope that that was a helpful and interesting, informative day for you. Now we've got a little bit more time than I thought we might have at the end to just raise any questions, comments or concerns that you might have. Okay, thank you. There's someone in the chat.
Yes, Milita is asking, what does it mean? Just a second, please. What does it mean to add white noise to data during simulations? I read it in one of your papers.
Excellent. Okay, thank you for that question. Good to hear that someone's been reading the papers, even if they weren't in the literature folder. So when we fit a regression type model, unless it's an absolutely perfect model fit, there's always some residual of the model, some unexplained variance. So just think of the residual as the information that can't be explained by the model. And often we assume that those residuals are normally distributed or a bell shape. And if we make that assumption, knowing the mean and the standard deviation, we can synthetically generate the distribution of those residuals, which we could call white noise. And we can take that synthetic representation of the residuals and add that back to our main model to capture the full variance. And that's not going to simulate the exact value on a day-to-day basis, because you're introducing some randomness from the white noise. But in the long run, in the mean, you're capturing the overall variance of the distribution. I don't know if that helped.
Thank you.
That's a tough question to raise and answer and listen to at nearly 4 o'clock on a Thursday afternoon, but well done. Any other questions?
At the moment, nobody's writing anything in the chat.
Okay, well, I think it's been a busy day for us all. Just a few final remarks, and then we'll just wrap up if that's okay. So just today, I hope that I've given you a taster, an insight into what it takes to set up and run a simple downscaling tool. And I hope that some of you in the room have been provoked into thinking how I might use this in my research. And I think there's certainly lots of opportunities for using this tool in Serbia, even looking at just the temperature data across the country and how we might use this to simulate extreme heat waves. So there are opportunities there. So if you would like to continue to use this tool offline, then please just drop me an email or get in contact if you're struggling. And remember my top tip: send me the PAR file if you're having any difficulties, and that will help me resolve them. So there's an opportunity to continue this, and I think in the next workshop with the other researchers, what we'll probably do is continue this journey, perhaps develop some scenarios for the future temperatures, and certainly move into how we use this tool for rainfall and extreme event estimation. So I think you'd all be welcome to join that, and you'd have a head start on the other participants because you've already had some exposure to the use of the tool. But we will develop some of the techniques further, implement some more sophisticated modeling than we've done today. So there's an opportunity to build on what you've learned today. And finally, I'd just like to thank you all for your patience and your good humor for sticking with it today, even though we're thousands of miles apart. And thank you to Biljana and Minucha in the room for being my virtual person in the room to help check the screens and assist. So over to you now then, Biljana. I think that's a good place to stop.
Yes, thank you, Rob, very much for this. For myself, I can say that I really enjoyed, but also I can see that students actually had a nice time, not only just by learning what you were teaching us, but because the exercises and everything was very interesting, and we for certain got some new experiences, and probably some ideas will be born during this workshop for the next paper. So thank you for this. We had the discussion time afterwards, after this part, but it seems there are no questions in the chat from the people who are not in the room. I think that this can be the end of our day, but hopefully we will see you tomorrow and the next days.